Hey, and welcome to this July 16th edition of the SkyTour LiveStream, coming to you live from the John Zach Memorial Observatory in picturesque northwestern Connecticut. Tonight, we're going to explore the beauty and mysteries of the universe, as usual, from stellar nurseries where stars are born to planetary nebula where stars have ended their lives. We'll see it all. As usual, we're going to learn about, see, and photograph these wonders live. Now, we can take questions from the chat room, so feel free to participate. If you want to see a specific object, let us know. If I can get to it, we'll check it out. If it's up, and it's all live, and it's all uncut. The telescope is almost ready to go, and we'll be up shortly. I'll talk to you soon. Hey guys, how you doing? Welcome to the stream. I'm actually just taking care of a few last minute details here before we get going. I do have a new microphone, as you can tell, so the sound should actually stay nice and steady throughout the night, but I have as a backup, I have the old system just in case this one fails. In testing a little while ago, it did fail, and I'm hoping that it won't stay that way. It will not fail for good. So we're continuing, and we shall keep going. Now, I will actually take us on a journey tonight. We're actually going to go to stellar nurseries because we don't have a moon, so I think we're going to be able to see some beautiful nebulae tonight, and we'll take some nice pictures of them and see what we got. So that said, why don't we get started? Now, currently, obviously, we're on Jupiter, and who can turn down a beautiful Jupiter, right? It's stunning. And I think the best thing that we can do is to just look at the fact that the cloud bands on Jupiter, okay, now the darker areas on Jupiter are called bands. The lighter areas are called zones. That's a little nomenclature that maybe you knew, maybe you didn't. But the lighter areas on Jupiter are interesting because with the Juno spacecraft, the imagery that we have been seeing from Jupiter is absolutely knockout, drop-dead gorgeous. And to that end, I'm very pleased with what it looks like. I mean, I'm really happy. You probably saw the images on my site, on my Facebook page of this, and you could actually see the clouds in their intricate detail. And I thought they were pretty nice. Now, what I did was I had the raw data, and that raw data was actually unprocessed. So I had to process it, and that's why you saw the difference in the imagery that you did see. So there. Now, I'm going to just shrink the size. I've got the chat window up as well. I could not get in touch with Amanda tonight, who moderates my stream usually, but she might be around at some point. And if it works, it works. Now, a little housekeeping. First of all, now Bill New York Skywatcher, P&K Space Imaging, and SkyTour LiveStream here with us, we are all now together under one global site. You can still reach us from where you are, from YouTube, and that's fine. But you can also find us by going to astroimaginglive.com. and you will see all 3 of our streams right up there on the screen. And these will be something that will allow you to springboard into each of our individual YouTube sites, and then hit escape or minimize, and it brings you right back to the Astro Imaging Live site. Now, there will also be a gallery on that site. It's already populated with some pretty cool things, and we are going to use that gallery in conjunction with the Facebook SkyTour LiveStream site to show the latest and greatest images of everything that we took pictures of that night. So I'm thinking we're going to go places with this, and we'll see. The idea is eventually we'll get someone else to pay for all the bandwidth and not have to ever make anyone else pay for that bandwidth. That's the goal. So you might hear me once in a while mention certain sponsors. Well, that's just business. But we're trying to do this because I'm an astronomer at heart. And in order to be an astronomer at heart, we have to be able to follow our heart. And we have to be able to, keep doing what we do. For those of you that see kind of in the observatory, you can see sort of the light here of this current, the current, let's see, well, I can't see it at all now. Okay, hold on, sorry. I guess I should have, okay, now I get it. I apologize. I was actually looking at something a little bit different. I'm behind on my own stream. Can you believe it? That's great. So, that said, what I was getting at was, you can see in the imagery with the cam shot, this telescope here represents several $1,000s of equipment. And no, I'm not going to ask anyone for money. I'm just saying that, we bring this to you without even thinking about charging you anything. And we're not gonna, ever. Just so you know, I'm also looking at some clouds. But we're going to get some views in before any clouds come in to ruin our night. And tomorrow night's actually going to be clearer, but unfortunately, tomorrow night, I'm on the Commander Cobra show on KGRA in the early evening. I might stream later in the evening. And then on Monday night, I'll be doing Fade to Black with Jimmy Church. And then sooner than later, I'm also going to be scheduled for the Richard Hoagland show. So I'll be doing that. Now tomorrow morning from, I guess, 11 to 1, yeah, 11 to 1, I will be doing the Paul and Ben Eno show, which is a, they're the Behind the Paranormal guys, and they are just incredible. And they've been good friends for many years. And we've done stuff together. We've done some interesting investigations together. And I think it'll be fun to do this, the 700th show for them. On their site. And that's 700 for them. And I think that's impressive. So, let me just take a look at my view here and see what I've got coming up. I want to make sure that we find some really cool objects to view. And I'm going to first look out the window, and the nice thing is that I can do this and my voice doesn't get any fainter anymore because I'm actually got this wireless mic. I love it. Yeah, I'm looking at a stellar nursery that's a little bit too low, but we can try it. All right, so let's see if we can find that. I've shown this to you before, but we're going to look at it again. In any case, I think that it's a good object to try and find. So let's go, and we're going to move there now. So moving. I apologize for the occasional buzzes from this mic, but it's better than hearing me in an echoey box, I think. If not, we'll change it. We'll go back. But right now, I like the sound. It's sounding better than it was. I'm just going to put the mic itself inside on an outside pocket so that it's... Yeah, we'll try this. Okay. Alright, let's try and get an image here that we can see. Oh, there we go. Alright, now this is something, as I said, we've seen this before. but hopefully we're going to actually be able to catch it in a little better light tonight. So let's do at 3.2 seconds. There's no moon tonight, at least not until way after midnight, so this is great. Let's do at an ISO of, say, 16,000. Let's shoot this at 3.2 seconds, and let's see what we get. Oh yeah. So let's take a look at what we just caught. Okay, this is, oops, that's not it. This is a nebula called Messier 8. It is the Lagoon Nebula. Ta-da! And I think some of you already knew that. Now, the beauty of the Lagoon is that it's a stellar nursery that has some very hot O-type stars. Remember O? O, B, A, F, G, K, M. O, our stars are the hottest. And I'm working on a system, by the way, so that I'll be able to actually circle and show you the stars live on the screen that I'm talking about. So that's to come. You see, everything is expanding and trying to make this a full-blown experience that takes us beyond anything that we're used to, especially me. So that said, if we look at this nebula, you see that we have that pink area. Now, there are several types of nebulas that are pink. In this case, we have this one. This is called an emission nebula, emission. These nebulae are mostly hydrogen gas, and the hot O stars excite the atoms and make the gas in the nebula absorb energy. The atoms in the gas, the atoms of hydrogen, absorb energy, go up to a higher energy state, and spontaneously drop it because they don't like being there. So when they do that, they emit light. That light just happens to be reddish pink, and that's what we see here. These are called doubly ionized hydrogen regions, or H2 regions. That's Roman numeral 2, so H2 regions. Moving forward, we'll spend time talking about H2 regions and what that means further. Now, I'm just going to bring up the chat here. I just see that I can't really see it right now, and I'm wondering where it went. I did have it. I know I did. There it is. Okay. Aha. Okay. So, that said, looking at this object, we know now that the red areas are areas that are doubly ionized, or H2 regions. Now, why is that important? It's important because the stars themselves excite the nebula to glow, and when they do that, they give themselves away. They show us where stars are being formed without us having to do anything more than just look for a pink object in the sky. And that's what we see here. So this region here is really kind of cool because, you know, that star you see right in the middle, that's actually a star that's a very bright O star, and it's actually responsible for lighting up this whole area, this whole nebula. Now, let's try one more picture, and we'll go a little. We're going to go down to 12,800 ISO, but take it up to 6 seconds. No, I'm sorry. We're going to take it up to 8 seconds. So we're going to take a little bit longer exposure. Here we go. So we're going now. So 3, 5, 8. Boom. We should be done. And now, take a look without the moon. Take a look at the beauty that we see now. This is just spectacular. This is really, really nice. And when I look at something like this, okay, to me this says, oh, it's so beautiful. Now, you'll notice also that not all of the nebula is pink. You actually see some blue areas. Now, the blue areas are a little bit different. The blue areas are areas where the starlight isn't being absorbed by atoms, but it's being reflected by micron-sized dust particles. So you get the idea. There's these reddish nebulae, and there are these blue ones. Blue ones, by and large, are called reflection nebula because they're reflecting light off of dust. Dust is reflecting light off of them. The red ones are called emission nebula. Now, emission nebulae come in several forms. We have three different kinds, actually. We have this kind, which is in stellar nurseries. We have the kind that are also in planetary nebulae, where you see a pink light in, say, the Ring Nebula, something that we saw previously. Now, the Ring is a stellar remnant. It's the remnant of a star that has died, and it actually shows us its chemistry by the spectra, the lines that we see when we look at the light from this nebula, and it tells us what's in it. And to us, that gives us enough information to kind of figure out what happened there and how this entire system came to be, where the nebula has a ring, a very pronounced ring, all right? And that is the planetary nebula. They call it a planetary, as I've told you a few times, because Charles Messier in the late 1700s decided that when he made a catalog of these objects, he wanted to make sure that they did not get mistaken for comets. And these were called planetary nebula because they could also be mistaken for planets because of their round nature, that type of thing. Well, it turns out that planetary nebulae come in many forms, not necessarily just round, as we'll probably see later. I am checking the clouds, and you know how it goes. As soon as we decide to stream, clouds go, get 'em, and they just come piling in. So we're still okay. So we're looking here at this, and we're looking at the Messier 8, the Lagoon Nebula in Sagittarius. All right, and now let's go north a little bit, because I'm going to show you a little bit more of the other nebula that I was telling you about before, the reflection nebulae. All right, and sometimes you'll see reflection nebulae that are also intermingled with nebulae like emission nebulae, and that's the kind of thing that we're looking at. You know, like here, this is now we're doing a 4K capture of this object at ASA 64,000 and doing a 4K shot. Now what I'm going to do is while we're looking this way, I'm actually going to take us a little bit north, and we're going to go to one other object that I really like, and I'm going to get there in just a second. Just selecting, and let's see if I can get there now. Go there. Okay, you ready? Here we go. Moving. To be quick. Up we go. Little squiggly lines. Alright, and now, let's see here. Okay, we got a little bit of issue with the dome. Let's just take a quick picture. We'll do a 2.5 seconds at 64,000. That'll be enough to just see what's going on. Yeah, it's there. Just gotta move it over a little more. Okay. Now let's do a little longer. We'll do 10 seconds at an ASA of, say, 10,000. 10 seconds at 10,000 ISO. ASA and ISO are used interchangeably, and sometimes I'll make the mistake of using them both. I apologize. So this is 10 seconds on the Trifid Nebula, M20, Messier 20, which is the designation given by Charles Messier. Now, look at this beauty. I mean, when you look at this, okay, you can see an emission nebula down below, and it has those dark areas are called dark lanes. Dark lanes, like bowling lane, except dark lane. And again, the stars in the center of the Trifid Nebula there that you see, there's a pair of them. Those are exciting the hydrogen atoms to glow, just like we talked about earlier. And above the stars is a blue nebula that's just a little bit farther up. And that blue nebula that you see, okay, which is up here, okay, this blue nebula is a reflection nebula. Now the star that's lighting this up is not powerful enough to excite the hydrogen. It's not, able to do it with high enough energy. So the dust grains that are all around all of these stars are reflecting the light back off of the star, from the star, and we see it. And that's what we see. So the Trifid Nebula is actually an interesting place because we see this guy down here, this nebula here, all right? This shows us some amazing features of emission nebulae and dark lanes. Now, those dark lanes, those aren't gaps in the nebula. Those are actually what are called molecular clouds. They're clouds of complex radicals and other chemical components, elements that are molecular in nature. So there's more than one atom, and they're actually in front of the cloud behind, and that's why they look like they're separating the cloud. They're not. They're just in the line of sight. Okay. So I think this is pretty interesting. M20 is really neat, and I think I'm going to take us now to another star-forming region that we've seen before. Okay, this is a star-forming region, the Lagoon Nebula that we looked at, the star-forming region. Now let's go to another one. Moving. It would help if I actually gave you a view. Okay, and what I'll do is I will run this. Okay. Now we don't see anything yet, so let me bring us down and do a 10 seconds at 10,000 again. That's right, Daryl. You can see M8 and M20 almost with the naked eye. That's correct. Now, we just saw that it was in the lower right area, and I had to move my chat out of the way. This here is yet another region that's very interesting. This is actually called the Omega Nebula. And the Omega Nebula is actually a very extensive cloud. It's actually, it's literally 4,200 light years from us. Okay? So now, knowing that it's 4,200 light years from us, if you could measure its size in arc seconds across the sky, we could then calculate how big it is in light years, and that's something that we can do if we wanted to. I'm going to save us from doing homework and classwork right now, because I just want to explore the beauty of the universe, and we can do this at another time when we start to get into something else. Okay, but this is M17, and in a way, this rivals the Orion Nebula, M42. Because if you've never seen the Orion Nebula, just wait until you see that in this camera. Oh boy. This is something that, when we look at this, under corrected sensor light, the light from the sensor that light the sensor is capturing, we'll see that it's probably more reddish. And it is a little bit more reddish. It shows up a little purple here, but it's really more reddish. This is another area of that's a star-forming region. It's being excited due to hot stars nearby that are exciting the gas and causing them to go up in an energy level and then spontaneously drop in an energy level, and this actually causes the emission of a red photon. Make that happen trillions upon trillions upon trillions of times per second, wherever the atoms are, and you get an overall reddish light. And it's just really, really pretty. Now, the Hubble Space Telescope looked at the Omega Nebula in detail, and what you can see is that there are some areas on in the nebula that actually have these little dark blobs. And what those are condensations of gas. What's causing it? Gravity's causing it. That is, there's something inside the blobs that are contracting and forming something. What is that something? A solar system, a star system with potentially planets, but at the very least, a star forming in there. And when we see a star forming like that, it's really a signal to us that this is something that the universe does in plenitude and constantly, and that's what's happening. We're seeing stars forming in this region. Now, those dark globules, they're actually dark, and you see them in other places in the sky, in other parts of the Milky Way, in other areas their stars are being formed. And they're named after a guy named Bart Bok, B-O-K. And Bart Bok, I met Bart. He was a great guy. He actually was one of my professors at one point. Bart Bok was actually a genius, and he discovered that these dark globules, which were remembered with his name, they're called Bok globules. These globules are areas where the stars are forming. And when we see them, and when we see these objects, we know that there's likely a solar system that's forming in there, a star system. So we think these are very interesting and have always been very, 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 very cool. Now, in this one nebula, there's 35 stars that you can't see, but they are at least 6 times hotter and 30 times more massive than the sun. Okay, so at least. So we're looking in the nebula where it's being obscured. The distant stars, the stars that are within the nebula, are being obscured. We can't see them. Excuse me. And these stars are very active, but we can't tell what they're doing because we cannot see them. We only see the results on the nebula itself. Excuse me, I'm going to take a Snapple break. Yeah, my voice. I've got so much speaking to do in the next several days that it's crazy. Like I said, tomorrow night, Monday at night, and then I inhaled a mosquito. That's really good. So you don't need to know that, but unfortunately, if you hear me gagging, choking, and if you hear a loud thud, then you know there's a big problem. Anyway, so let's do one more shot of the Omega Nebula. I want to do a longer one. I'm going to say 20 seconds at ASA, just slightly under that. I'll go 8,000 ISO for 20 seconds. Okay, here we go. Okay, we're taking the picture now. And keep in mind that when we look at nebulae like this, we're actually seeing them in the past. We're seeing this nebula as it was 40 to 100 years ago. So the stars that are obscured now might not be obscured, you know, in 4,200 years when the light finally comes to us and reaches us from there. That's beautiful. Now, it's a little bit bright because we are near the horizon with the Omega. Excuse me. And let's see if I zoom in. Okay. Yeah, see, our stars are pretty nice looking. I think we can probably serve to do some focus here. So I'm going to try and get us some critical focus, if you'll bear with me for a second. I want to make sure that we do that. Alright, we got that. 1 second. So, what do I mean by critical focus? Well, we can certainly focus the telescope, but what we want to do is we want to focus the telescope so that it's absolutely perfect. So to do that, we take a star and put it in the center of the field, okay, like this one, and we zoom in for as much as we can with the camera, and then we go to our focus system, which is on the hand controller for the telescope, and we move it out until it's unfocused, and we move it in slowly. And there we go. So that'll be the best focus for the evening. Now, is that a perfect focus? Maybe, maybe not. But let's do another 10 second at 8,000 shot, just to see what we got. So it's taking a picture now. And let me know how the sound sounds. I mean, hopefully the sound is a lot better. I made sure I had lots of batteries, but I actually have one 9-volt that I found for this. I've got to get more. So this is 20 seconds at 8,000, and let's go back to this image here and zoom in a little. Oh yeah, look at that. That's really pretty. I see that I actually have I have it a little bit too low. So let me bring it up, and now I'm going to do a 12,800 photo at less than 20, so you don't have to wait that long. We'll do 13 seconds at 12,800 ISO. So now we are going to go to another nebula that is right above this one, and I wonder if those of you in the chat know exactly which one it is. I bet you do. Those of you that are familiar with the night sky will certainly know what's just above this that we're going to go see. But I'm checking the focus right now. Oh yeah, see right in the center there, you see those stars? Okay, those stars are beautifully focused. Those are good focus. So this is nice. Now, here, what we're doing is we're doing moment-to-moment shots. We're just showing you a few images, and we get the images. We put the images up, and you can see them right away. You see exactly what's going on. But the bottom line is that if we take a look at this, there's a lot of information in this photo. There's a lot of signal, but there's also a lot of noise. What's the noise? The whitish background. Ideally, the background should be what color? Black. Okay? So to get it looking more like it's supposed to, we can actually take a number of photos. In fact, a bunch of photos. We could take a bunch of photos of this, say 10, and then we can actually stack them together. I've talked about it before. And we end up with a stacked image at the end. Now, every image we take tonight, I will put up on both the Facebook site, the SkyTour LiveStream Facebook site, and I'll put it up on the astroimaginglive.com, our clearinghouse site, where Paul, Keith, Bill, and I are doing our live streams. And just another word about that. Bill's stream is wide-angle sky views for looking for meteors and satellites. Paul and Keith do planets and the moon. I do nebulae and deep sky wonders. So I think between us, I have the most work, you know, to be honest. Because I can't just show you things and then leave it and then not tell you what it is. You want to know. You want to hear these things, I think. So I have to be, you know, I have to be careful, and I have to tell you everything that's going on so you understand. And I think that's a fair thing to do. Oh, thank you, Dee, for telling me that it sounds good. I wanted to make sure that the sound is good. All right, now let me do one thing here. I want to go to full screen mode, but I also want to bring in the. Let's see here. I want to bring in the chat. So 1 second, please. Is this it? Well, it was. Let's see here. Hang on. Almost there. Why is it not letting me do that? Come on. Okay. When I go to full screen mode, it doesn't allow me to show the chat at the same time. And I don't have anyone here tonight to help me with the mod stuff, so I'm not going to be able to monitor like the way I wanted to, but that's okay. I don't care. We'll just make it happen, right? We'll do it any old way we need to. All right. So that said, I'm going to move this over here, and it'll take up a little of my screen. But you know what? The extra light from the screen, not being in full screen mode, allows you to see more in the observatory with the other light. So that's cool. Okay, so this is another, the Omega Nebula then, M17. This is one where star formation has taken place. But I gotta tell you, it's possible, because we haven't seen anything else like these, other than these black globules that we saw there. We haven't seen any additional evidence that other star formation is going on. So it's possible that star formation has ceased in this nebula. So it could be a H2 region that's in decline, okay? And that's a possibility. Now, let's go to one that we know is not the case. So I'm moving there now. Okay. Now let's do 13 seconds at 12,800 and see what we get. Now, this is north of the Omega Nebula, just slightly, and it's actually a very interesting place, because what we're looking at in this image, and I gotta just move it up a little for us, and move it over a little, and we're gonna take a little bit longer exposure. What we're looking at is actually we're gonna do 20 seconds at 12,800. We're looking at another nebular region that is fairly well known, and what this is actually called the Eagle Nebula. And I know that there's a number of you in the chat that actually wanted to see the Eagle before. Believe me, it's the coolest thing. It really is. So we're looking at the Eagle right now, and the Eagle Nebula is oh yeah, look at that, huh? Let's go back to that. Now, I actually swatted a mosquito, and it's right over my Eagle Nebula, so I'm going to have to just clean my screen a little bit. Sorry about that. Oh, this is nasty. Sorry about this. Hey, Rockstar, what's going on? Welcome to the SkyTour LiveStream. Yeah, that's cool. Alright, wipe off the mosquito, and now, I don't know if you can see it, but can you see the the pillars of creation? They're within the glow, but if you look at it, you can actually see that that you have these bright areas. In fact, I'm going to move the telescope to get a picture of this. We gotta be able to do this. I want to show you this, and the way to do this is actually to take a longer exposure, but knock down the ISO sensitivity just a bit. So I'm going to go down to 8,000 and go to a full 30 seconds, and I'm going to move this up just a little bit. I want you to see this. Okay. I absolutely love this nebula. Again, a star-forming region that's, you know, somewhat unparalleled. It's not as bright as the others. It's not as bright as the Omega, but it is actually as prolific. It's actually fostering many stars, and the Eagle Nebula has been the subject of the Hubble Space Telescope. If you look up pillars of creation and look at that Hubble photo, you will see the pillars of creation. Okay, and let me go and see what we got. Let's see what we got here. Yeah, right in the center. Actually, I'm going to zoom in a little. I had to go down to 8,000 so you could see this easier. Now, when I come up with this, right there in the center, do you see those little dark areas? They're kind of diagonally, they go diagonal from the lower left to the upper right. There's a big one in the center just below that bright star. As a matter of fact, that bright star is just below another one that goes from the lower left to the upper right. And then below that star, there's a big one that goes from lower left to upper right. And then below that one, that dark area, there's one that goes from the lower left to the upper right. These are the pillars of creation. Phenomenal. These objects that are creating the stars have this incredible chemistry going on inside of them, and it's something that, you know, we just don't have a good feel for as human beings, but as astronomers we do. We kind of have an idea of what's going on there. Now, it's really easy to find, and its brightness is 6.4 overall. Now, what's that? That's a magnitude value. The magnitudes are values that are assigned to the brightness of objects that we see in the sky. They can be somewhat dim, or they can be very bright. Vega, for instance, is magnitude 0. The sun is minus 26. Okay, they go negative for the brighter. And this is 6.4. So you see, it's not terribly bright, but it's also, it's not, in other words, it's not a naked eye object except in the darkest of skies. So, but let's talk about this. It's 7,000 light years away. Okay, And at 7,000 light years away in Sagittarius, it's actually in the Sagittarius Carina, like Eta Carina is a star, and Carina is a constellation. But in the Sagittarius Carina spiral arm of our galaxy, there's a Perseus arm, the Orion spur, the Orion arm. There's different names for the spiral arms in our galaxy that we've identified, and this is in the Sagittarius Carina spiral arm. Okay, part of the spiral arm, and that's the next arm inward, closer to the center of the galaxy from us. Okay, so we're seeing to the next spiral arm when we look at this, which is really cool, and that's 7,000 light years. All right, now there's several more spiral arms, and then the center of the galaxy is kind of in this direction, and it's kind of hard to see because you actually are peeking between clouds and around the edges of stars, and then there's a little tiny window through which you can actually see what we think is the closest view to the center of the galaxy we can get, which is not the center of the galaxy at all, but it's the closest we can get. So now, if we look at this some more, what's interesting is the stars that are in here, okay, are only about 5.5 million years old. They're young stars, okay, and the hottest stars are O-type stars. In fact, O6. Remember O0, 1, 2, 3, all the way to 9. These are the hottest stars here are the O6s, and they're responsible for exciting this nebula. In fact, it's, if you think about the way hydrogen gas will get excited by a hot star, it's actually the high energy ultraviolet that these stars give off that excites a hydrogen atom like that. And the hydrogen atom says, oh, give me that energy, and it sucks it up and it says, I don't want it anymore, and like I said, instantly. So it comes up and it goes down trillions upon trillions upon trillions of times all at once, and you get the overall reddish glow. And that's pretty cool. And it happens on an atom by atom basis across all the atoms in the nebula. Fascinating process. Now, those O6 stars, though, are probably not going to live more than a couple 100 million years. So, they're moving through their life fairly swiftly, but they are the brightest things in the universe. You know the old saying, right? If you burn your candle twice as bright, you live half as long. And in Blade Runner, in the original Blade Runner with Harrison Ford, you hear that said. It's actually, they burn twice as bright, but they're beautiful. The replicants are beautiful. In the time that they are here, the most beautiful thing there is. That kind of thing. Well, the same thing here. The O stars are the hottest, the most beautiful, but they're the most short-lived. And you can see now, right in the center, you can see that the dark molecular clouds and the dark dust, that stuff is in the foreground, and it's obscuring the hazy nebula behind, and that's what we're seeing here. All right, and that nebula is actually backlighting them, so we can actually see them very, very clearly. I'm really happy with this photo. I think I can do a little better. If we do a little shorter exposure, let's do a shorter exposure, and I'm going to do a shorter exposure, but we're going to do a little bit, I'm going to do a 15-second exposure, but I'm only going to do it at ASA 4000. No guarantees here, but I'm trying to get that happy medium between contrast of this object in the sky with the darkness of the nebula. Maybe we'll see something, maybe we won't. But this is 15 seconds at ISO 4000. And what do we got? Oh, look at that. That's interesting. We might have been, yeah, see? We're a little bit successful there. See that right there? You can actually see that now. You can see this. You'll have a chance to play with this image yourself and compare it to the previous image. Now, at an ISO of 4000, we don't have as much noise in our final image. In the old days, they called that film grain, and the grainy photos were the result of fast exposures, fast, high-speed exposures. We don't have that here. So this is pretty cool. Now, it shows pretty nicely. Now, let me see, again, if we can do one better. Let's take it to 25 seconds at ISO 4000. Again, lower sensitivity but longer exposure. We're trying to see if we can eliminate that bright background, and if we can, then this tells me this is a good setting for us to actually use moving forward and actually taking serious pictures that we'll be able to process, you know. So let's see what we got. Let's see if that gave us anything else. Oh yeah, look at that. Now look at now. You see that? You can actually see far better. You can actually see that central, sorry, I bumped the microphone because it's hanging off in front of my face. That there's a bright star kind of above center, and just below it you see that dark molecular cloud from the lower left to the upper right. You see it a little better now. All right, and this is prompting me to do one more thing. It's not even too bright, so I'm going to actually go up in the ASA to ISO to 5000 and go up to 30 seconds. So we're basically, in camera language, that gives us 2 more stops. All right, so a full 30 seconds at 5000 ISO sensitivity. Now, the one thing that I think you should do is go look at the Pillars of Creation photo taken by the Hubble, and you'll enjoy seeing that, especially when you compare it to what we did here from our little earthly telescope. It's not going to look, oh, you know what, I just realized there's a cloud in front of the nebula right now. Sorry. Well, why are these clouds here? It's ruining my night. It's ruining your night. Let me see if we got anything anyway. Oh, yeah, see, this is looking good, but we're getting this grainy, that whitish haze we're seeing. Yeah, this is actually from the cloud that's like between me and that thing. I did not want to cut this stream short, darn it. All right, let me look in the sky. Let me do an assessment. You know, I know that it's supposed to be clear tonight, but why? It's like all of a sudden we got clouds everywhere. Man, I'm telling you. All right, so where can I go? What can I look at? Ooh, that might work. Okay, so we looked as promised at stellar nurseries, areas where stars are being born. What I'd like to do is take us to one more location that, again, we've seen it before, but it really has a poignant meaning now, because stars are born, and here they are. Now, stars that are masses like the sun, okay, they live a different life than stars that are much heavier than the sun. Stars that are more massive than the sun are like O stars and B stars, okay? A stars and F, G, K, those can all be similar masses, but O stars tend to be very, very massive. And those are stars that are not to be trifled with, because they don't live a long time, and when they blow, when they end their lives dramatically with a supernova explosion. I'm looking up in the sky now, seeing if I can, why, you know what, you gotta understand something, folks. When I'm looking at the sky here, I see, for instance, I see the clouds, and they were going a different direction, but I think as soon as my observatory dome opens up, the clouds go, it's open, quick, crowd them out, crowd them out, cloud them, first one there wins. And it just stinks. But here, I'm going to go to now a area that we have seen before, and let me see if we're at this one, if this guy that I'm trying to look for is going to be in a place that's visible, or is it going to be cloud covered, for crying out loud? Let's see. I don't know yet. Let's find out. Just a sec. Bear with me. As Hal says in 2001, just a minute. Just a minute. So let me zoom in here and check that out. All right, let's go to this guy and let's see if we can see it. Oh, we might be in luck. It's under some faint clouds, but we'll take a look anyway. We'll see what we can do. Sorry, folks, I hate clouds. I really do. They ruin everything. Tomorrow night's going to be great, but I can't do it, unfortunately. Let's do a recording here at higher ISO. You can see the object now on the screen. We've seen this before. This is called Measure. This is the wild duck cluster. Okay, Measure 11, I believe. Let me just go. Now this guy. Let me take a nice photo of this. I'm going to come off. This is a 4K recording I was just doing. All right, so that was at ASA 32,000 that I was recording it in 4K. 4K, by the way, stands for basically double HD. It's twice the HD resolution. It's a very high resolution. It's the highest current active resolution that we can use. There are some 8K experiments going on, but this is the pretty much the highest that you'll find out there actually. So let's do 5 seconds at 8,000 ISO for this and see what we get. There's a little cloudy area there. It's going to be through clouds, but let's see what it does. That's why only 5 seconds. Okay, now even through light clouds, okay, this is what we get. Now this is what's called the wild duck. This is not a globular cluster. This is actually just a cluster of stars that started its life in a H2 region. Remember H2, the pink nebulae? It started in an H2 region back when it first started. And you say, well, where's the gas now? How come I don't see any? How come I don't see any gas anywhere? And the reason is because the stars have long since, with their stellar winds, and like the sun has solar wind, the stars have long since blown all that stuff out and away. And of course, stars are moving through space. And these stars are all kind of mutually gravitationally bound a little bit, so they're actually moving together through space. And they may have left the nebula behind as they blew it away with their high pressure winds. So we see that here. Snapple break, hold on. And we're seeing now stars in the midst of their lives. All right, we see where they're born. This is now places where they live. They may migrate apart further. And when they do so, then you might have individual stars sitting out in space where there's planets, and there's like a place like Earth, that may form around one of those stars, along with a complete solar system somewhere along the way. That's entirely possible. So this is the wild duck cluster. Gives us a beautiful view of stars that are in the middle of their lives, stars that are actually in the process of just being stars. Now, it's really one of the most stunning, and it's called a compact open cluster. Clusters like this that aren't globular clusters, but are like this, have like 50 members, 30 members, 25 members. These are called open clusters, and so this is an open cluster, but it's a compact open cluster. They haven't migrated out away from each other at this point. They may, okay. And the thing is, the diameter you see here on the screen is about 1/3 the size of the full moon. Okay, so that's how much space it takes up in the sky. You can kind of see M11 with your eye in a dark area. It's pretty cool. And it's actually 14 minutes of arc in diameter. Now, 14 minutes of arc in diameter is an interesting number to play with, because we know that if we take with 14 minutes of arc, we know we can actually do some operations on that, can't we? Remember I talked to you about doing the calculations? So some of you remember that little formula perhaps that we had. And basically, and I have it, I've actually programmed it here, and I may do it, but I'll do it a little bit later. I just wanted to tell you, we can actually calculate the actual size across. It's 14 minutes of arc across, and there's 60 seconds per minute of arc. So basically, we take 14 times 60. You know, 10 times 60 is 600, and 4 times 60 is 240. So all we have to do is take 840 seconds of arc and put that into our angular separation issue that we did before. So let's do that. You know what? I'm going to do it. So we had, what did I say, 800 and angular separation is 840, say, seconds of arc. And the distance to this object is a problem. The distance is 6,100 light years. Okay, so 6,100 light years at a distance, 6,100 light years at with a separation in the sky as we see it of 1/3 the full moon, or 840 seconds of arc. Let's do that real quick. And what do we get? We get 6,400. And now if we calculate that, it tells us that it's 26 light years across. All right. Now, if we want to do that in terms of AU, that's basically 16,482. Oh no, it's not. It's 1,648,288 astronomical units. So you see, 93 million miles, the distance from the Earth to the Sun, becomes a cumbersome unit when all we're trying to do is like figure the size of a cluster in the sky. Now, that calculation that I gave you, which is 26 light years across, it's almost exactly 26 light years across, tells us, you know, how far the stars have spread since their inception, since their birth. All right, and that's pretty cool. Now, what I want to do is take us to another object, and I've not been killing time, but I do have a clear window, and I'm going to make use of it now. I'm going to take us a little bit up in the sky some more, because now we've seen stars in the midst of their lives. We see stars here with a 26 light year cluster, and let's see if I can bring you to this one to show you more. And it may or may not be in a cloud, but let's go. Okay, moving. Oh, we might be lucky here. Now, sometimes stars will actually migrate away from their previous location, as we talked about. And that migration that we see might take the form of stars that simply have moved out of the area, because stars have their own motion through the sky. That's actually called proper motion. Let's just take a quick 5-second photo at an ISO of 8,000. Okay, here we go. This will show us some stars that are here. Now, what you're seeing here, this is actually a well-known object in the sky, believe it or not, these little tiny stars. These are called the coat hanger, and they're actually a small cluster of stars, okay, that actually was formed in a nebula at some point and migrated away. We actually have a little bit of cloud covering it, so we're not really seeing it as best we could. And the coat hanger, the coat hanger is actually an area in the sky. That's actually the full coat hanger right there that you're now seeing. Okay, that's we have to just be, yeah, that's what we're seeing. I'm gonna just take a quick shot. Sorry about the noise. They keep shunting people down the road. Still, they got, you know, construction going on. 2.5 seconds at 8,000 ISO right now. And let's see what we get. Okay, that's about what we want. So now you can actually see the coat hanger. It's a little, basically a triangle. Okay, and this is a small collection of stars. It was a small cluster when it was formed, and then it became, it went out on its own, basically. It went on its own to make something of itself, I guess. All right, kind of cool, and I thought I'd show you that because that's another set of stars in the midst of their lives. Now, let's go to one other place here. Moving. Alright, now I'm going to take a quick photo of this to verify I'm where I believe I am. Okay, this is going to be a quick photo just to see. There we are, dead center almost. I'm just going to bring it up. Okay, now, when stars die, what does that mean? What do you mean die? Well, stars are big balls of plasma, hot gas, and these balls of plasma actually are doing something called nuclear fusion. They are taking hydrogen atoms in general, and they're going through a process to make them into helium atoms. Okay, it's a process. Now, this happens in stars like the sun, and they can get to carbon and sometimes a little farther on down, silicon. And when stars do this fusion process, when they start running out of hydrogen, they start fusing the next thing that they've been making a lot of, and that is helium. So they make helium into carbon, and then there's a lot of carbon kicking around. And then they make nitrogen, and then they make oxygen, believe it or not. And this, in stars like the sun, we don't ever really get into something called carbon, nitrogen, oxygen, fusion mechanism. Okay, where the star will make carbon, then nitrogen, and oxygen. Okay, that's something that happens in more massive stars. In stars like the sun, we basically start making helium, and that's about where it ends. Okay, for us. Okay, 4 seconds at ISO 8000 of the Ring Nebula. But when it runs out of hydrogen, a star like the sun will end up having an issue, because it's not going to be able to maintain its size any longer, because there's an outward pressure. That's radiative pressure, it's called, pressing outward, pushing outward. Okay, stellar wind, you might say, solar wind, we know about. And that solar wind that we see is something that will maintain the diameter of the star, because the whole time it's pushing outward, the star itself is trying to contract because of its own gravity. So as a star tries to collapse, that radiative pressure outward pushes outward, yeah? And that is called hydrostatic equilibrium. It's an equilibrium point. Now, if a star gets out of equilibrium, something changes. Either the star grows or it's going to get smaller. Now, typically, the star will initially get smaller because something stops working. That is, the fusion process maybe that creates hydrogen, creates helium rather, may stop. Okay? And I'm going to do a little longer exposure here. I'm going to go 8 seconds at 8,000. And if we look at that and we take the next step and go, well, now what happens after hydrogen is used up? Well, now there's no more equilibrium. The star is now going to have a problem maintaining its size. So what happens? It begins to shrink. As it shrinks, what happens? The core gets hotter than before. And when it gets hotter, the star then expands again, because something in the core happens called helium flash. The helium that was in there, which was not hot enough to burn into carbon and other elements, now does so. And that flash is a whole renewed energy source for the star. And as such, the star begins to grow again. Now, the problem is that when that star begins to grow, there's an awful lot of helium around. And if you think of onion skin, that's what we think about stars as, onion skin layers. There's going to be a shell around the core of helium that's being burned into carbon and other elements. On the outside of that is hydrogen, remains of hydrogen that is not contributing anymore to the major fusion process. So what happens is the star expands, and the outer envelope, that we call it the outer envelope, the outer gases of the star, move outward along with this expanding star. And then when the star begins to use up its helium, it begins to contract again. However, because the outer envelope of the star has moved out so far, the objects, the gas out there, is being pushed outward by the still present radiation that's pushing outward. And so it keeps going. Gravity can no longer pull it back to the star. So we get what's called a sloughing off of the outer layers of the star. And that's exactly what you're seeing here. You're seeing a star that sloughed off its outer layers. And in those outer layers, there's other elements. There's not just hydrogen. There's also oxygen. There's other elements. There's carbon. There's some nitrogen. There's a little I said oxygen. There's also hydrogen in there, and there's some helium in there. Because a star isn't a perfect mixture. A star sometimes has other elements that are in its atmosphere that are kind of mixed in, and that's what we're seeing here. So when the star sloughs off its outer layers, what's left behind is a hotter core, and that hot core can serve to illuminate and energize the atoms in this gas, and that's what we're seeing right here. We're seeing this central star that you can see right there in the picture, right there in the middle of this nebula. That central star is actually causing this gas to fluoresce like this because the atoms in the gas are absorbing at a particular wavelength that they like and then spontaneously re-emitting the gas, re-emitting a photon. And it doesn't do it in any particular direction. It does it any old way, any old where, as a former physics professor of mine said. It emits it in a direction that's any old where that it wants to go. And when it does so, we see it in the color that makes sense for that particular emission sequence. All right, that energy state they're called. So from one energy state to another, whenever a photon is emitted by an energy state from this location in the atom to this location in the atom, and I'm just saying that, a higher to a lower state, that particular energy state always is a photon of a certain frequency. Okay, here we see in this M57, the ring nebula, Messier 57, we actually see that higher energy state to lower energy state transition that we're watching literally right here, happening right before our eyes, that energy state is a fairly straightforward one. And so we see a little reddish area around the edges, which is probably doubly ionized hydrogen that you know about as H2. All right. And then we probably see some hydrogen and helium in the middle that's being excited and doing more emission. And as we look at this object, we have to keep in mind that this planetary nebula, the nebula itself represents a second method by which a nebula can be made to glow. The first one is the stars that highly excite with their ultraviolet radiation, that excite the atoms in a nebula, and we get the H2, that doubly ionized hydrogen. We call those the stellar nurseries. This is not a stellar nursery, but it is glowing nonetheless. Okay, this is a dying star, so it's glowing for a very different reason. It's glowing because the white dwarf in the center that you're seeing right there, that is a white dwarf, by the way. That star in the middle, which is fairly faint, that star is actually causing the nebula to glow. Why? Because the outer layers are sloughed off. And now all that's left is the hot core, which is doing the last few gasps, so to speak, of a process of generating some type of chemistry in its core. The star is going to continue to cool. The processes are going to stop. Everything that's happened to the star, that's going to happen to the star, has already happened. This here will be here forever. Now, when the star actually cools to the point where it's no longer able to excite that nebula, guess what happens? The nebula just fades away. So we're looking at a nebula that's going to go away. It's not going to disappear. It's going to continue to expand because it's several light years across here as it is. It's going to continue to expand, and it's going to move farther out and disperse itself into the interstellar medium. And the elements generated by that star won't be lost. They'll probably go into making a planetary system somewhere or a new star. And when that new star is formed, guess what it's going to have in it? All the elements that we see here. It'll have the helium, the oxygen, the nitrogen already in its atmosphere. Our sun came along 4.5 billion years ago. The universe is 13.8 billion years. So if you do the math, you find out that the universe existed for 2/3 of its lifetime before we ever showed up. So when the sun was formed, it was formed out of a rich assortment of materials and elements. So the sun has a tremendous chemistry, a tremendous number of different elements in its atmosphere. And many of them are elements it can't make, but they just happen to be there because the sun had them when it was born, when it was formed in the solar nebula 4.5 billion years ago. So that's what goes on here. So when we see this, we see the stars when they're formed. We see stars in the middle of their lives. In fact, all around this nebula are stars in the middle of their lives. Okay, those other stars you see are, all right. And then we have a star that is ending its life, and we see the nebulae associated with the end of the star's life, and we call that star death. Now, of course, they're not really alive, but they are. We're seeing the life and death of the stars here. So I think that's pretty cool. I don't know if anyone has any questions about that out there in the chat, but I'll be happy to entertain your questions if you have any questions now. We actually have quite a few clouds out there, which were not there. We had totally clear blue sky when I started the stream. Of course. But I hope you guys are having a good time. I think that it's really, it's pretty cool. And I see, Curtis, you're saying, the red is harder to see because the camera is probably not modified with a different filter. H alpha's in the red. Yeah, actually, this camera doesn't have blocking filters. Okay, this camera is what's called a full aperture camera. All right, it actually has only a sensor, and that's the only thing that's exposed. There's no glass filters. Those are called blocking filters. What he's referring to is ordinary cameras. When you shoot with regular cameras, the ordinary camera will not see some of the infrared and some of the ultraviolet. Okay, it only sees the visible part of the spectrum, and it tends to have these little glass filters in there that block the frequencies. This camera does not. When you take this cover off, if I take it off the telescope and you look right inside, you're looking right at the sensor. There's nothing between the sensor and the stars. All right, so we're seeing the full Monty here. We're seeing the full thing, just without any kind of blocking of any of the frequencies. Now, the sensor itself is sensitive to a little bit of the infrared, a little bit of the ultraviolet, just like all other cameras. But you can't actually see the infrared full, all right? Because this is not something that the cameras are designed to do. Now, we have infrared systems. I actually have one on a drone. It's a full, true FLIR, forward-looking infrared system, which actually, when you look at it, it's pretty cool. And Sherry, yeah, you know what? You can put questions in caps, Sherry. That's great. Great idea. Yes, and right, your third guy, yeah. Your cell phone will have a little blocking filter in it. Yeah, it's called a blocking filter. So when the camera reads out the image, what it does is, you actually you have a. I'm sorry, I was just looking at Rockstar. Very rare that I see him swearing. No, and the reason that Caps was helping me is I don't have a moderator tonight. See, and I'm looking at this from across the observatory. So if I see something come up that has a question, okay, I can tell the difference. So, that it helps me if it's in caps. So I'm sorry that's if you don't like caps. I know it sounds like your people that someone's yelling when they're doing it, but it's a functional reason for doing it tonight. We won't do it every night. Only tonight. It helps tonight because I'm on the other side of the observatory looking at the screen. So that said, as I said, when we actually when we look at you know what? I forgot where I was. Son of a gun. Sorry, I was doing 10 things at once. I apologize. If someone can just remind me where I was. Man, I hate that when I just don't know what's going on sometimes. Anyway, and someone will remind me. You know, I know I'm kind of a little flighty sometimes with this, but oh yes, thank you for reminding me. You said A7, and that makes me remember now. Yes, there is no blocking filter on this, Curtis. It's an A7S2, and it's not the telescope. I'm sorry, the camera is not just stock. Okay, we've actually done a few mods to it ourselves, and I think it's important because, you know, I think it's important, you know, to understand that. Well, first of all, for me anyway, you know, I've got all this equipment in here. I'm not just going to put a stock camera on the telescope. I'm going to have to make some mods to make sure that it works the way I want it. And so we've actually made some changes to it. And Ronald, I can see your question from across the observatory. Thank you. It says, how big was the star near its end? You know what? Good question. Now, we don't know what stellar type the star was originally. We know what it is now, but we don't know what it was then. So that said, when we look at the star now, it was most likely, because it's a planetary nebula, we know that it did not explode in a supernova, or it's not a binary system, so we didn't see a nova or a type 1a supernova. I'll explain those at another point. But what you would see is you would have seen the star would have been bright red, like Antares in the eye of the scorpion in Scorpius. Antares is bright red because, of course, it's a red giant. That's what this star would have been. It would have been a red giant, and then as the helium shell that was fusing to carbon and other elements deeper in the star started to die out, the star would again not be able to maintain its size. It would collapse under its own gravity, but the outer layers would already have been liberated and freed from the gravitational influence because they're being pushed out by what was remaining of the radiation pressure. Okay, and the term for it is radiation pressure. That's a better way to think about it. So when the star was actually collapsing, it would actually make basically another shell on the outside of gas that no longer has a home, not bound to the star. That's what we're seeing here. All right. So it was a red giant, and it could have been, yes, Ronald. Yeah, it could have been huge. As an example, if it was a star like the sun, okay, the sun is 864,000 miles across. This, you know, could have been, it could have actually been 180 million miles across. So it could have actually come out to about the Earth's orbit and swallowed the Earth in just a little bit more. So maybe it could have been about 190 million miles in diameter. That's what this star could have been. And then it shrinks down to a white dwarf, which is a mere fraction of even its original size. And all that's left is this very hot surface material, the degenerate material on the surface that's extremely hot. And if it was a binary system, then it might actually be pulling material from the second star that it's circling. And when it does that, there's an interesting thing that happens when a mass of more than, say, 1.44 solar masses lands on the white dwarf. The white dwarf basically has a spastic reaction. It explodes, and that shell of hydrogen gas or whatever that's on the surface of the white dwarf gets blown off. It's almost like the white dwarf shakes it off and then continues its you know, post-star existence. It continues doing what it was always doing. Now, when it blows that off, the star gets to a certain brightness, and that's the intrinsic brightness is called luminosity, and I'm going to use luminosity more often. And so the star would get to a certain brightness if it does that. Now, that is called a nova. Okay, it's called a nova, and a nova is not a supernova. A nova, yeah, Chandrasekhar limit, yep. And a nova is actually the result of what happens when the 1.44 solar masses of material, as we've found, gets on top of the white dwarf. Okay, and gets collected onto the white dwarf through this mutual sharing of material. Now, as I said, when it blows that off, okay, the parent star that's feeding the material may survive, and you might just have a nebulae nebula forming around the star, around the pair of stars, and it doesn't blow them away. So it's pretty cool. So yeah, in fusion, third guy, you're asking, in fusion, atoms are fused together, adding protons and neutrons. Well, in a sense, because what happens is, okay, to get a different isotope, that is a flavor of an atom, you would add neutrons, right? Add more protons and you get a different atom, but add more neutrons and you get a different flavor of the same atom. Those are called isotopes. So deuterium is one such thing. Tritium is one such thing. That said, that's what happens. And now Ronald asks about the can precious metals be formed during this type of process? Actually, precious metals like gold and some other materials really they're made more in supernovas, okay? Because regular stars that burn and fuse hydrogen into helium, like our sun, those types of stars actually never get past iron, which is number 26 in our periodic table. And so, excuse me. So when you see a star that's like our sun, you know that you can never expect to get basically gold out of it, unless it was formed with gold from another star system. When a nova goes off, a supernova rather, then interesting things happen, and I'll explain that really fast. When you have a big heavy star, like an O-type star, let's say, or even a big B star, okay, further up the chain in the main sequence that we call the hydrogen to helium burning stars, they run out of their hydrogen very quickly. And when they do, the reaction tends to stop very abruptly. Now, it's not an easy path like our sun will take, where it slowly runs out of hydrogen and then the helium shell just sort of kicks in over time, flash occurs, and then over a million years or so, the sun will expand into a red giant, okay? It's not like that. The star is burning fast and furious for its life, and then all of a sudden, it stops. Bam! What happens? Gravity takes over. There's no more outward radiation pressure. So, boom! Down it goes. It collapses. And when it does, there's nothing to stop it. And what's at the center of these hot stars? What's at the center is an iron core that can't be made into anything else, in the normal fusion process. Now, just as an aside, there's only two ways that fusion occurs in stars. There's the hydrogen to helium process that we talked about, okay? And then there's the CNO cycle, where carbon makes nitrogen, makes oxygen, and they all feed off of each other. It's called the CNO cycle. Those two processes take place in stars. CNO cycle is for larger stars, and the PP chain, or the proton-proton reaction, which is the hydrogen to helium thing we're talking about, that takes place in stars like the sun. All right? So, that in mind, something interesting is that when we have these stars, the bigger stars doing the CNO cycle, and we have an O star that's now unable to do anything for energy production, and it collapses like that, the collapse is catastrophic. And the star can collapse in seconds. And what happens is that gravity tends to pulls the star together, It gets extremely hot, hotter than any temperature that it was doing, hotter than any temperature that it was using during its normal main sequence lifetime. So, when the star begins this collapse, there's a catastrophic process that occurs. And if you can see it, you're in danger, okay? And that goes for us here on Earth if it's something nearby. But that is this. As it collapses, all that material in the outer star, again, this trillions upon trillions upon trillions of atoms, heavy mass, many times out of the sun, is being collapsing onto that iron core, that that immutable iron core. When that happens, something even more incredible happens. That particular rebound, that is where the mass all hits the iron core at the same time, because it's a sphere, and it collapses onto the core at the same time. That collapse causes a massive explosion, and when it rebounds and bounces off that core, that's when the pressures and temperatures are reached to make the rest of the periodic table elements. And I say rest, but research indicates that some of those elements are actually made by neutron stars, which merge. And neutron stars could be the result of, a collapsing. I believe it should be back up. Don't know why it stopped. I have greens everywhere. I have all full green. So I'll assume that we're still going strongly. Let me know. I'll wait. The alien's got another one. No, I don't think so, Maureen. But that's funny. So I can still see the chat, and we are up now. The stream is back up. So I'm not sure what that glitch was. I have very strong internet, and we are indeed back. Okay, thanks. Thanks, Ben. So, anyway, when that explosion occurs and that material just blows off of the star, it's a catastrophic explosion. And that's where we get a lot of those elements. We get, like I said, merging. We get merging neutron stars that cause further element production. And we also get additional elements created via other methods, and those methods, we'll get to at some other point, I think. Now that I'm looking up, I'm seeing we have a potential clear area. So I'm going to do something crazy. I'm actually going to look for now a supernova remnant. Okay? I think a supernova remnant is kind of a cool thing. I really like to do that. And I just want to look right outside now real quick and just make sure that I'm not telling you a lie. Oh, I might be telling you a lie, but I mean the stars are actually, the clouds are actually still there, but they're dissipating a little bit. So we could probably wait it out just a little bit longer and see, because now we have a perfect opportunity here to look at another supernova remnant. I don't know if we're going to be able to see it. It's in the constellation Cygnus. It's called the Veil. And I'm looking up, and I see where the Veil is from here. And I don't know, it might be, it's just in the border of some clouds that I think are moving in another direction. But we'll try. What can I say? We'll just try. And if it doesn't work, we'll look at something else in the meantime, and we'll come back if the clouds do indeed go away. I love the fact that they may be going away, though. I like that a lot. Let me just drop the volume of the music just a little bit. Okay, so I'm going to go here to this. There's a special star in Cygnus that is called 52 Cygni, and it's actually on the border. I'm going to go there now, moving. Okay, let's just do a 4K. We're going to do a 4K vid here, and we're going to pump up the ISO just a bit. Okay. Yeah, alright. Okay, down at the bottom there, that's 52 Cygni, so I'm going to bring that up. Okay. Now I have your chat like in the way here, and I just have to move you guys down for just a couple minutes. Oh boy. Okay. So, alright, 52 Cygni is a star that just happens to be coincidentally along the path that the supernova remnant has taken through space. And so let's see if a 13 second at 160,000 ISO setting can show us anything. It's a little bit in the cloud, but it might be a little white to view, but we're gonna try and keep at this. I'd like to show you. Oh yeah, it's just a little too much. Want to try and keep at this so we can actually see it. We just might have to wait for a second or two for the clouds to actually leave. And yeah, I'm still waiting, sorry. Snapple break. Made from the best stuff on earth. Okay. All right, okay, we're going to be not going to be able to do this right away. We're going to have to come back to this to try it a little bit later, because the cloud heard me say I want to go look at it, and it said, "Oh, quickly go there." Just kidding. So I'm going to look and move to a different object. Oh, maybe. Sorry about the buzz. The buzz is just, you have to live with the buzz to get the good voice. Hang on one second, let me look. Oh, you know what's clear? Alright. What's clear is something else that might be fun. Let's go check it out. Okay, so just a second, folks. I'm looking at it now. I'm trying to find it. Yeah, that's right. That's there. Right, Cassiopeia. And okay. Here we go. Oh yeah. Now let's go check it out. Okay. Okay, we're gonna move now, and we're gonna move to something else. This is on the more northern horizon, so it's gonna be faint, but let's try and bring it in. Okay. Yeah, there it is. Let me just once it beeps, we're gonna move up. It beeped. Did you hear it? Now we move up. Okay. Now let's do a photo. Again, we're at 16,000. We don't need to be at an ISO of 16,000. I think we only need to be at an ISO of about 8,000. No, 6,400. All right, and we'll do 5 seconds at 6,400. Here we go. And this is going to be something interesting. Okay, this is a beautiful, beautiful cluster. And it's a cluster that some of you probably already know. And I'm sure you're writing it in chat now, aren't you? Just like going to town. This is actually the double cluster in Perseus. Now, the double cluster in Perseus is really just probably the most famous cluster in the sky, because it looks like two nearly identical clusters. And let's go back to the main view for 1 second. And now what I want to do is I'm going to move us over. Okay. And now let's do a 4K video just of this little area. Okay. You'll notice that there's a slight change to the aspect ratio. And now when we just increase the, the sensitivity a little bit. Okay, now we're at 80,000 in our 4K. Look at that. You can see the cluster right there in front of you. It's beautiful. Stunning. And this cluster, okay, this cluster actually is 6,800 light years away, and they're paired in the sky. They're just about the same distance each from us. 6,800 light years, 6,800 light years. Absolutely amazing. And now let's go down and let's actually do a another view of the cluster. Let's go down to say 2,500, and let's do a 13-second exposure at 2,500 ISO. Okay. So 13 seconds. So here we go. And let's see what we get. Bam, that's beautiful. You know, and again, this is an example of a cluster that has had that formed with another full cluster of stars in a nebula at one point, and then they ended up migrating away. You know, and so it's pretty cool. Now, we talked about NGC numbers and Messier numbers, the M number. Well, these don't have an M number, they have an NGC number. And the NGC number for these is 869, okay, and 884, okay. So they're low numbers because they were among the original ones found. So let's try and go up on the ISO sensitivity to say 8,000 and do the same 13-second exposure. Sorry about my coughing. I apologize. One thing you guys need to understand, if I didn't tell you already, I have my right vocal cord is paralyzed, and that happened after I had surgery 2 years ago, 2.5 years ago now. And during that surgery, while on the table, there was a clot that got away from them, and they ended up, it ended up giving me 6 strokes. So when I woke, I was a quadriplegic and I was quite blind. So it was a little odd waking up, going to bed feeling, going to sleep normally and waking up unable to move and unable to see. And that lasted for a few terrifying days. But as time went on, I started getting something back, a little bit here, a little bit there. The best thing was I got my sight back to the point where I can actually drive now with no problem. And this can happen to anybody. I just happened to be, that guy who had it happen to him. This is beautiful. Now you can actually see the double cluster, and you'll see now. See that orange star? Isn't that cool? In the center of the view, there's actually an orange star, and I'm going to zoom in on that star just a bit. So look at that star. That happens to be one of 2 orange stars in this cluster. The other one is, let's see if we can get to it. I don't know if we can see it. Can we see it? Yeah, there it is. Over on the left, just above the small window there, you can actually see the orange star, the other orange star. Okay, and that's 2 of 3. Over on the right, just to the left of the number 1246, you see the 3rd orange star that's there. Now, if you keep looking, you'll see even more. Okay, now the orange stars, are interesting because they tell us that those are stars at a different potential location in their evolution. Maybe those are orange giants. Maybe they're K-type stars, which are just before M, which are red. The K's are, this kind of color. So maybe that's what we're looking at here. Either way, we're looking at a really fascinating location in the sky. And so I wanted to show you the double cluster anyway. But this is, again, an example of stars that are living out their lives in the middle of their lives. Okay, we saw the birthplaces, we saw the ending places. We're seeing a little bit out of order too, because we have to go where the sky is clear, tonight. So this is neat. Now, now we have to see I want to show you the catastrophic end for stars, and to do that, I have to try and view this supernova remnant. In the winter, we'll be able to see one that's really, really obvious. Well, with a telescope like this and the camera we have, it's obvious. And we're clear now, so we're clear for that location. So I'm gonna go to that location really quick and get us to that location. By the way, this is Perseus, where I told you the double cluster is. This is actually in the Milky Way, because the Milky Way goes through Cygnus and all the way down through Cassiopeia and through Perseus. Okay, and what is the Milky Way? The Milky Way is the spiral arm of the galaxy that we see. Okay, one of them, and there's several that we actually see spiral arms, and we're actually seeing the spiral arm here as we move through, and one of them is of course called the Perseus arm. So now let's actually go to this other remnant that I wanted to show you. Here we go. Now, I remember that star 52 Cygni that I talked about? We're going to go to that star again. Okay, actually, we're going to go to the Veil. The Veil Nebula is a supernova remnant, which is notoriously hard to photograph, just so you know. It requires an awful lot of work to try and do it, but not shrinking from the potential, I'm going to try and show it to you. And oh, I can see that we're right on the border of a cloud still. Okay, came kind of, yeah. That's 52 Cygni you're seeing down there on the bottom. Right, came a little bit too soon, I think, but you know what? Why not try? I think we might be able to do it. Let's try it, shall we? Okay, 13 seconds at 8,000. Let's try it. 13 seconds at ISO sensitivity of 8,000. Here we go. While I'm trying to search for the veil here, oh, you know what? It's there. Okay, you can see it. Okay, that's 52 Cygni. Now, if you look at this really closely, you can actually see a little bluish haze going from that bright star at the bottom, moving up to the upper left of that star. Okay, you're looking. That's part of the veil, that part of that supernova remnant. Now, this actually worked out pretty well. So what I'm going to do is I'm going to go right up to 30 seconds at 8,000 to see if we can see anything more. All right, so it's underway now. Now, the veil supernova remnant is indeed the remnant left over by a star that didn't just die as a planetary nebula, but it died in a catastrophic explosion that probably took several systems with it when it went off. Now, the veil is a massive remnant, okay, and as far as distance, it's actually only 2,600 light years from us, okay, and at 2,600 light years, oh yeah, this shows better. At 2,600 light years, you can actually see, oh yeah, look at that. If you look in the just above the star, you can actually see. Well, somewhat above the star, you can actually see that wisp. There's a very sharp wisp. Let me see if I can zoom in. Okay, right there, centered. There's a vertical wisp that you can see right there. That's actually a fairly bright area of the veil. Pretty cool. Yeah, and then down here is 52 Cygni. Now I'm going to go and do this again. And I'm going to do it at 16,000 ASA. So it'll be a little brighter image, but we're also going to see potentially a much better view. Maybe not. We're just trying. We're trying everything, man. We're trying everything, man, to do this. Yeah. Okay. So the veil again was probably the result of an O star that exploded, maybe a very massive B. We can't tell what the progenitor was. That is what the star was. Yeah, it didn't look like we got much more bang for our buck on that. But again, that star at the bottom is a star called 52 Cygni. You can actually see right here. You can actually see some of that wispy nebulous matter going through the center of the view vertically. That's actually pretty cool, and I'm really thinking that that's a pretty good view. Now, as I said, the remnant is notoriously hard to photograph. But I think we can. I wonder if we can try. That's about the best we can do, unless I actually take it a step further. We could probably. Now, if I did the piggyback and did it zoomed in with a telephoto lens, unfortunately the telephoto lens is not a 10-inch diameter like this is, so it might not see it at all. But sometimes wider angle is better. But in any case, when we're seeing this, you know, and it says so even when you look at it for observing purposes, it says the nebula is notoriously difficult to see visually, even though it has a bright, you know, integrated magnitude of 7. What's that mean? It means that the star, the whole nebula together, if you could count, pull them together in one area, it would be magnitude 7. But it's not really that obvious. It's not really that bright at all. And in a dark sky, this might show. When I get the observatory to Arizona, this might be a very different matter at that point. So we'll consider that for a future date. Now what I want to do is, in keeping with some, with the planetary nebula that we were talking about, the stars that die a more gradual death. And I'm sorry about that stupid person who keeps doing that with their car, saying, "Wow, listen to me, listen to me." This is where I wish I had I wonder where he is. I'm wondering if I can, I could actually magnify a laser beam, put it through the telescope, aim it at him, and say, "Cease your operations." And it's like, scare the crap out of him. That might be fun. Anyway, let's see now. Looking at the sky, gotta see if we can see. Okay, that's Altair, and it's got a cloud in it. Let me see now. Ooh, okay. Let's try that. Let's try. Where is that? I'm just looking at something right now just to see where it might be. Okay, that's going to be. Ooh, it looks like it's going to be. I was looking for the Saturn Nebula, which is actually in some clouds, unfortunately. But let's keep looking around. You know what? Let me look up too. I want to look up because I know we've been focusing on star birth and death tonight. Shut up, you idiot. All right. I'm sorry. Did I say that out loud? Let's try this. I'm going to I want to go back to my list of planetaries that I've assembled here. And I want to try and find a couple that I know you'll like. If you're thinking about, let me try this one here. See where we are. Center this guy. Okay, all right. Now this one. Okay, this one actually. This one will work. Okay, this one's called the Blinking Planetary, and we're going there now. Okay, now I'm going to do a 4K video right here live so we can see what's going on, and I'm going to increase its sensitivity. And now, if you'll notice, below center and to the left, and I'm going to move it in now, there is this little blue object. You see it down there? That little blue object is called the Blinking Planetary. Now, it's called the Blinking Planetary for a very interesting reason. It doesn't actually blink, but it appears to blink when you look at it, because your eye, when you try to look right at it, it tends to not appear the same way as when you move your eye to the side. Because when you move your eye to the side, the the receptors in your eye don't see it the same way as it sees it when you look straight at it. Okay, it has to do with the way the rods and cones receive light. Okay, now let's take a photo of the Blinking Planetary. This is again a 4K video, but let's get out of that and let's do not 30 seconds. Let's do 10 seconds at an ISO of, let's say, 8,000. And you'll see that, to the camera anyway, the Blinking Planetary is actually pretty bright to the camera. Alright, so I just realized the dome was a little bit in the way of the telescope there, so I don't know how that's going to look. Okay, that's pretty cool. So let's go look at it. So there's the Blinking Planetary. Now, if we zoom in a little bit, look at that. Look in the center. what do you see? You see an interesting little star, don't you? That star is the star that is actually the cause of, and Jesus. Did you ever wish to see an accident? I mean, I'd probably start clapping, you know, and it'd be on the stream. Yay, I'm clapping. Somebody just like put themselves into a tree, you know. But they take advantage of the fact that, you know, this road is being just temporarily used, and it's a fairly long road. As a little aside, look, don't worry, I'm getting back to the blinking planetary in a second. Don't worry. But as an aside, I think what's interesting is we can actually put spike strips out there, and they could destroy their car or their motorcycle with spike strips, and I could say, oh yeah, I'm sorry, I guess, yeah, I had them there, I apologize. I didn't mean to throw them out there right at the last second as you were about to drive by. Oops, I guess I did. Oh well. But you know what? I probably am not going to do that because, you know, I'm not really that kind of a crazy person. Okay, let me go back to the blinking planetary here for 1 second because I want to actually see something. Okay. Now, here's what's interesting, and I think I got about as close as I can get with this right now. Yeah. When we're looking at this blinking planetary, you notice how it actually has an interesting, you see the white central star, but you also see this little white area that kind of goes diagonally to the lower left and the upper right. You see that? Okay. That actually is pretty significant because that shows us that this planetary is actually something called a bipolar planetary nebula. And no, it doesn't mean it has, you know, occasional problems dealing with people. It means that it actually has a tendency to have more material thrown through its north and south polar regions. And that goes back to what happened when the star was actually there, when the star was actually a full size. Now, it's actually you know, the star at the, you know, if you stare at that planetary central star, okay, in the telescope anyway, that's what gives it the description of a blinking planetary. It's because the blue nature of this planetary nebula, it begins to fade from your vision because the blue light is not, your eyes are not very sensitive to that part of the blue spectrum. So you see it kind of fade a little bit, all right, and that's really cool. And that's why it's called the blinking planetary, and that's the more active reason. Now those things that you see out to the side there, the white ones, they're actually not really white, they're kind of greenish. Well, those are actually called flyers, which means fast low ionization emission regions. I know you all want to remember that, so I'll say it one more time. They're fast low ionization emission regions. So it means what happens is that these are objects that are moving away from the star, the central star, at supersonic speeds, okay, which to a star is not a big deal. Okay, this thing is 4,000 light years away, and based on its size, we could calculate how far across it is, but we won't do that now. It's 2.1 arc minutes in size, so multiply that by 30 arc seconds per minute. I'm sorry, 60 arc seconds per minute, and then do the 206.265 thing I told you about, if you remember it, and do your calculation. Some of you out there may actually do this. I used to have to do this all the time, you know, because those are kind of like bare minimum stuff that we would just do. So the reason I took the exposure at this setting was so that we can actually see that central star. Otherwise, it would just be blue and overpowering. But this is a little tiny planetary nebula, like the ring, okay, like the dumbbell we've seen before. And the ring and the dumbbell are actually, you know, kind of like near each other in the sky. But the ring and the dumbbell are also, they're generated for a different, from a totally different mechanism. This one, again, sloughed off outer layers, but maybe the star was rotating rapidly, or so, and maybe that rotation causes the bipolar appearance of the material that we see. You know, with those things. Now, north and south to a star doesn't have to be up and down in our view. Obviously, it can be anywhere. As I told you, I had a physicist guy that told me that, professor, and so they could be anywhere. And then the thing is, in this particular case, they're to the lower left and upper right. Really, really cool. I like it very much. So now, let's go back to our list of these little planetaries and see if we can do something else. See if we can find another one. This is one that, let me center it and see what we got. Okay. We're going to try this one. Okay, this one is one that you know, we've looked at it before by request, but now we're going to go to it again. Oops, sorry. I'm moving the dome the wrong way. Okay. Yeah, this is... Oh yeah, we're in the clear with this one, so this would be a good one. Okay. This one that you don't see because I don't have the camera live, sorry. Sorry about the noise. Alright, this guy, let's do, it'll be 10 seconds at 8,000. So let's do that. 10 seconds at 8,000, off we go. This is called the Cat's Eye Nebula. Alright, and the cat's eye is going to look extremely similar to what we just saw. Okay? And now I'm doing the same settings as before, and you just saw it briefly. You saw it briefly there. Okay, now let's zoom in and see if the same settings for the picture that we took before can show us a central star in this guy. And the answer seems to be that it cannot. Now, that means, let me see, I don't know if you can see the central star there. I'm on a kind of a monitor that probably needs some help. Let me take a quick look here up close on the monitor. Yeah, you can still see it, but you know what I'm going to do? I'm going to kick back the exposure a little bit, and instead of doing 10 seconds, I'm going to come back to 6 seconds at 8,000. Here we go. Oh, what will we see? Oh boy. So now we should be able to see that star with a little more clarity if we just turn the brightness down a bit. Alright, and so let's bring it up. Bring it up. Move over to that star. Move over. And move over. Oh, you don't see it, do you? It's there. You know what? I gotta even do a lower exposure than this. And this is kind of cool. And I don't mind, if you don't mind, trying to find the right exposure. Let's go back to, let's just do 3.2 seconds at the 8,000. Okay, let's see if that shows us. Okay, you notice now the stars don't even show up as bright. Okay, and let's do this. Sorry about, I'm hearing the buzzing too, so I'm sorry about that. Let's see what we got here. Okay, you know what? I just realized there's another thing we can do, which may be very, very beneficial. And that is, we can, whoa, look out, man. See, if I touch the thing, it made this really funky noise. I see what we need to do. I'm gonna take down the ISO to 4,000 and go up to 15 seconds at 4,000. That's probably too high. What am I doing? I'm trying to make sure we can see that central star. Now, this nebula here that we're looking at, this is 3,100 light years away, so not very much different from the other one, which is 2,700 light years away. Okay, so that's why I picked this one to show you next, because they're actually kind of similar. Okay, but they're in totally different parts of the sky. This one's in Draco, and the other one was in Blinking Planetary was in Cygnus. Okay, here we go. Let's zoom in. Let's go over. See what we got. And there we go. Now you can see that when we do it less sensitivity, you can actually see the central star. So you got it? You see that nice central star in there. That's so you basically we're tuning the exposure to get the best detail. Now there's not much more. There's not much more in this. There's not much more in this that we're seeing. Okay, so this is pretty much what you see. Even with the Hubble, it looks it looks phenomenal with the Hubble, but here the best earthly views kind of do look this way. Kind of cool. But again, it was like the blinking planetary, very similar. The cat's eye is. So if you think it's just the cat's eye is the only thing like it, well, that's actually not true. And that's what we're looking at right here. So I think it's kind of a neat place we've gone to here. We're actually kind of close to the zenith here, and there's a lot of stuff over our head that might look really cool. And I'm gonna at some point, I'm gonna not tonight I don't think, but I'm gonna go to the wide angle because I do want to show you the night sky without the moon. And we're going to wait until Cygnus and Vega and all those constellations are at the zenith, kind of at the start of things without a moon. And I think that's going to be much better for us. All right, so let's see now. Let's go to another object. Now, again, we're looking at, tonight has been stellar nurseries, stellar death, and stars in the middle of their lives that were born in large nebulae. And that's just what we're seeing so far. We also tried to look at the supernova remnant, the Veil Nebula, and it's kind of an unsettled night with the with the sky. When I look up right now, I see the Milky Way, but it's not as bright as it has been before. So we'll keep trying at it. Don't worry, we'll keep trying. Okay, now let's go down. Let's go back to these planetaries again. And let's see, now we did the cat's eye. Now we're going to go to this one. This is another one that you think you saw before. But you haven't. Okay. You'll think you've seen this before, but you haven't. Okay. This is actually, well, of course, right now you just see nothing, do you? I get that. I know. All right. So, let's do a 4K video just to see what we have here. All right, now let's see where it will be. Okay, this one is 2,533 light years away from the solar system, and it's actually fairly dim, so we might be pushing our limit. But let's try it anyway. Let's try it. Okay. And let's do it at 10 seconds at, come on, I'm sorry about this buzzing. I'm probably not gonna like that for much longer. Meaning I'm gonna get either rid of the system or do something else. Let's try it at 51,200 ISO. Here we go. 10 seconds at 51,200 ISO. I'll be coming back to chat in a minute. I can see it from here, but I can't read it right now. Oh, let's see now if I can see it in there. Yeah, I think that's not be it. What I'm looking for is something called the Blue Flash Nebula. Suffice it to say, I found it one night and it looked pretty much exactly like the rest of these. But I just want to show you to just give you an idea. Let's do 10 seconds at 10,000 ISO. Okay, did we get it? Yeah, I believe that little guy is it right there. It's showing up consistently with those little wings on it. We don't actually have a photograph of it to compare to, at least in the system I'm using. So, but I want to show it to you. It really should be a little more blue, but that could be because of its almost stellar appearance, and that makes sense. But let's see now. Let's go to a couple other things. Jesus. Yes. I don't know why people think that muscle cars are important, but I don't know. To each his own, I guess. Okay, where is this guy? Let's see. No. Okay. Hang on a second. I'm just going to come back out. My search I said I wanted to look at that, and it didn't show it to me. Let's see the object info. Okay. Okay, we're going to go to this other one, and I'm not sure if we'll see it very well. Yeah, it's really down in the murk. But I don't know. We might luck out. The problem is that we're getting some dew on the telescope, and that's going to completely limit what we're going to see. But if I've got a clear sky, then I'm going to fight through that, and I'm going to do something to help figure that out. Okay, so I'll tell you what I'm going to do in a minute. So I'm going to go and crank this up. And what do we got? Yeah, we have got a problem. That's what it is. Okay, so here's what I'm going to do. I have a little emergency kit here for handling dew on the lens. It's only a stopgap. It's only something that lasts for a few minutes, maybe longer. But I'm going to do it. And it's actually a very specialized piece of instrumentation called a hairdryer. So I apologize for the sound, but let's put up with it for just a couple of minutes. Oh, I would if it would work. Son of a gun. Oh, that was just nice. This it figures. Just a sec. That's amazing. You know, even when I want to make something work, it doesn't want to go. It's hold on, folks. Oh, hey, look at that. Sorry about the noise. Sorry about the noise. I'm just trying to get it to just de-dew our lenses here. The end of our lens has actually got quite a bit of dew on it, and it's going away. You may ask, well, doesn't that heat cause any additional problems for the telescope? Yes and no. It gets rid of the dew, that's a problem for us, but it also causes us to heat up the telescope, and you might say, well, isn't that a problem? As I said, and well, that is the problem, that it heats up the lens system a little bit. as long as we don't overdo it. Hey, did I say overdo? Yeah. So then we come back on the temperature a little bit, let it cool back to more of an ambient. That's what I'm doing now. You can't really see it on the observatory inside cam. I'm sorry, but okay. I believe that is good enough for now. So this goes back in there. Now let's see if we can. Now you see how many more stars are visible just right off the bat. Okay, no space in the memory card. Oh, that's just what I need to hear. Okay, now what I'm going to do is hold on. Okay, we're going to delete this guy. We don't need that. Okay. We're going to delete that. Sorry, doing some housekeeping. Nothing to see here. Talk amongst yourselves. Just kidding. Okay. So now, let's do another 10-second at, well, not this size. Let's go 10-second at 16,000. Let's see what we get. 10 seconds at 16,000 ISO. And the object, again, that you didn't really know you were going to, is something called the little dumbbell in the constellation of Perseus. And let's see if we caught it. It's right there. I'm going to bring it up. Okay. Okay, and now we'll just go over a little bit. Let's do this again. 10 seconds at 16,000 ISO. And this is called a little dumbbell for obvious reasons. It looks just like the dumbbell, but a smaller version. So, there we go. Now let's go look at it in detail. So, here it is, the little dumbbell. And you'll see that I've got it on too high a ASA, too high of a sensitivity. So, that's actually crippling our view. Let's go to 4,000 and go to 20 seconds. You ready? Here we go. 4,000 ASA, 20 seconds. And we're going to look at the Little Dumbbell Nebula. Yes, indeed. Again, the Little Dumbbell is a remnant of a dead star, a star that has passed, died. Now, stars, of course, don't die and live like people, but of course they do have, we call them lives. Now, let's zoom in on now, and you'll see a very different image. So, this is at 4,000 ASA. Now, you can actually see the little dumbbell actually has some color in it. You see that? It has some red fringes. Now, I want to stay at 4,000, but I don't. I want to go up one level. I want to go up to 5,000 ASA. And I want to go to 30 full seconds. Okay? Now, that's going to take a while. I'm sorry. 30 seconds at 5,000 ISO sensitivity. Now, the little dumbbell is this planetary nebula in the constellation Perseus that's really interesting. It's 5,600 light years away from us. All right, so as such, it really is incredible. It's actually 2.7 by 1.8 arc minutes in size. So I think that if you want to do your calculation, you can figure out how long it is, which is kind of cool. So let's go and zoom in on this here, and let's see what we got. Now you can actually see, you can see some of the colors a little better. I see that it's so small, that the camera sensor has a problem, but also the other thing that has a problem is that the telescope needs to be guided a little better when it's at these angles. So you see the stars are a little bit elongated. That doesn't happen in general, but it does happen when we go to low angle stuff like this. But you can see the color still, and that's kind of cool. And like when we defocus the star images to see the color, if we do a slightly defocused nebula, we can also sometimes see the color better. And if you look at the direction the stars are moving, they're moving kind of across the screen, right to left, left to right, right? And it's dragging out the color of the nebula in a similar direction. So we're actually getting more color for our eyes to see. So you see more reddish at the top and a lot more at the bottom than in the last exposure. And so that's something that is interesting about these objects when you do this, okay? So that's another technique that we use. Sometimes we don't actually see things focused. Sometimes we only show them in that regard, so we can actually see them. As they may appear slightly blurred. So this is another planetary nebula, and because I never say die, I'm gonna go back to, or take a picture of, bring us to the actual Dumbbell Nebula. Here it comes. This is very close to being at the zenith. So this is, again, another stellar remnant, the result of a star that has sloughed off its outer layers and died. So now we're going to do this again. We're going to take, we're going to pull back. We're going to do a 10-second at 5,000 ASA exposure, just to it's called an acquisition image, just to see that we have it. Then we're going to change the settings and pull it in closer. I'm sorry, closer to center. Oh, look, that's pretty good. And we already got a pretty good view. Nice, not bad. I'm going to just bring it up a little bit. Here we go. Okay, just brought it up a little bit, which didn't show on your screen because I was doing it through the camera. So now that I know that we've got that, let's now take a exposure that is 20 seconds at 5,000. Okay, and actually no, 20 seconds at 3,200. So we lose 2 stops by going from down to 3,200. Okay, from 4,000. I'm sorry, 5,000. We go 5,000 to 4,000. That's a stop. 4,000 to 3,200. That's another stop. The stop is a sensitivity range, basically. Okay. Now at 3,200, let's do 20 seconds. Okay, and let's see what we get. Again, the Dumbbell Nebula is a bipolar planetary nebula, a nebula that actually shows these tufts off the top and bottom that are really fascinating, and they're there because of the nature of the star that created them. Maybe the star was a rapid rotator. We don't know. Okay, but if you take a look now at this image, this is an absolutely beautiful image, and the central star is quite visible. Here it is. Check that out. This is a stunning photo. I'm like, wow. I can't believe that we're seeing this. I can't believe that it's showing as well as it is. But it is just really spectacular. Look at that. You could see convolutions in the nebula. You know? And this was this image was taken, what was the settings again? 20 seconds at 3,200. Okay, I'm going to do another one. There's another 20 seconds at 3,200. We're going to actually do a full-blown astronomical image tonight. That is to say, we're going to take all the photos. So, that is to say, we're going to take a number of these of the Dumbbell Nebula like this, because it really is coming out gorgeous. Alright, that's beautiful. And we're going to do it again. Here we go. My goal is to try and show the dumbbell with some of its attendant polarity, bipolarity wisps that show up in red in the nebula. And the central star is really quite obvious. And when you can see the central star, it's at the zenith. The sky has cleared beautifully up there. So we can actually see this very clearly. And I'm going to do another one, and I'm going to do only 2 more after that. Okay, and then we'll move on. But I just wanted you to see this because it really is stunning. And here I am. I'm not even showing it to you. Oh, don't worry. I'll show it to you. And you're going to have access to these photos, by the way. I'm going to put these up so you can get them and do your own processing on them. Okay. Now, if you want to learn how to do the processing, that's another thing that I can teach you, and I will teach you. And if you don't want, if you want to just look at things and be amazed, well, then great, because you know, that's why I'm into this, because I too was amazed at the Dumbbell Nebula when I first saw it, and I only saw it as a hazy patch in a telescope. Okay, this that we're seeing here is really stunning, and let's just go into that for just 1 second, just to show you. Okay, look at this detail we can see. Oh, okay, we got a little movement there. I see that we have some movement. Interesting. I don't think we had that for the other shots, did we? Let's go see, because if we did, here's another one. Yeah, no, you see what happened was I actually bumped the telescope, apparently. And that's deadly. So now we're going to delete this image. And we'll take another one in its place. I might have been a little too close, and I might have actually bumped it just enough. We're at enough magnification, so that can make a difference. That can make a difference. Again, 20 seconds at an ISO sensitivity of 3200. Yeah, and it's just beautiful. Now let's go into this one, make sure that it didn't do that thing to me again. Yeah, no, we're good now. But check that out. Look at the complexity in the bottom of that nebula, the bottom right. It's reddish, and it's actually got a tremendous amount of knottiness in there, complexity. That's something that shows up actually on other images as well. And I think it's important to understand that this is something that is systemic to these kinds of nebulae. Okay, that shows you that the star itself wasn't perfectly homogeneous. Okay, it wasn't perfectly filled with the gases, and they weren't perfectly distributed. There was something going on. And what we find in these red giant stars is that these red giants actually have a very convoluted surface. Now, when you watch a pot boil on the stove, it boils through a process that you know is called convection. Well, the big giant stars that slough off their outer layers are typically fully convective stars. They're actually, from the core outward, they're just bubbling out this stuff. Okay, this stuff. And as it does so, this material coming out from the inside of the star isn't necessarily material that's very homogeneous. It might be different. It might have some peculiar, higher density areas and lower density areas. That said, when we look at the resulting planetary nebula that forms from stars like this, okay, it tells us something about the progenitor, that is the star that made it. And that, what it tells us in this particular case, is that the star itself, as a red giant, probably had a very strange surface. It probably looked like if we want to put it in terms of, say, a piece of fruit, it probably looked like an orange with warts, okay? Meaning that there was some large protrusions of gas and plasma coming off the top of this object, of this red giant star, inside, from inside, the processes going on inside. That said, that tells us that red giants many times do have a very non-homogeneous surface. They have these lumps and bubbles, bulges sticking out of their surface. So they're not round like our sun. They're not spheres. They can be kind of bubbly looking. They can have this blistered look to them. And there are areas that actually have a very different, one more. There can be areas that have a different density, different material. Okay, and then when that happens, the stars, when they do form off this sloughed off nebula, then what you get in the nebula kind of mirrors what happened in the original star. Areas that have this higher density material might have a higher density element on the shell that's outside in the planetary nebula. When we look at the ring nebula, okay, it's fairly smooth and it has some bipolarity to it, okay, and that bipolarity is seen in the edges of the ring nebula. When we look here at this, let's see if we got that movement again. I gotta be careful. When we look at this one, okay, let me go to this image. Okay, I guess better. Okay, when we look here, you actually see the bipolarity, across the top and the bottom, right? But notice that it's like an hourglass figure. Notice at the narrow parts of the hourglass, to the lower left and upper right, you can actually see a hazy, hazy inclusion of other lighter density, lower density gas in there. Again, this tells us something about the star that made this nebula. It might have been that the star was a rapid rotating star, but had some type of processes that were causing more material to come out of the north and south pole areas of the star. And it probably is north and south pole. And it could also be, just to be clear, it could also be the east-west rotation that's spewing out more stuff and the poles minimally. So that it can happen that way too. So it's a science in and of itself to figure out how planetary nebulae form. And it would have been a really interesting thing that I would have liked to have gotten into, but I chose exoplanets instead, because exoplanets to me were the future. Planetary nebula, well, those are death. Okay, star death. And we know enough about our sun to know that we've got to leave our sun before the next 5 billion years gets here. Otherwise, we're going to be done for, because it's going to expand into a red giant, which will eat the Earth. Okay, Snapple break. Yeah, this is this regular Snapple iced tea. It's really good. Okay, now let's go to another object. The sky has cleared nicely, and I'm looking now for some additional objects that I'd like to show you. Oh yeah, okay, you know what we're gonna do? We're gonna go back to the Eagle Nebula, and I'll tell you why. It's in a better part of the sky. It's in a very dark area of the sky, or darker area. And I think that we might be able to actually get a better view of it. So hopefully you're okay with this. I know that it's we've seen it already, but we have other things we can look at if you want to. And that's the other thing. I will come into the chat here shortly and take a look if you've got anything you want to see. Okay, moving. Okay. I figure if the dumbbell nebula can look this good, then the Eagle's got to look just as pretty good, And I think we're fairly dew-free right now. Let me just confirm that. Yeah, we're starting again, but it's okay. It's not a lot, and that's good. Okay. So if you're up for this, we're gonna take a look at the Eagle again. So hopefully you are. If you're not, let me know. But let's see here now. Okay. I'm gonna take a exposure of this now. Let's go do this. All right. So to do this, we want to do. Well, first of all, we want to move it over. So let's just move this over here a little. Yeah, sometimes it doesn't quite align, but you know what? This is 20 seconds. I'm going to do 20 seconds, yeah, 20 seconds at an ASA, 25 seconds at an ASA of 3200. Let's just try it. Don't know what we're going to get, but let's find out, shall we? We'll do this together. Now, one funny thing that I want to tell you is that in learning the periodic table of the elements, we actually learned there was actually a funny song to remember every single element in the periodic table of the elements. And I had to do a conference a couple months ago at a place called Pine Bush, and Pine Bush, New York. And I was going to sing the Periodic Elements song, but I just didn't have it in me to do it. I wasn't brave enough to do it, and I've since forgotten some of it. But it's a really funny song, and there's two versions out there, and the one I like better starts off. There's hydrogen and helium and beryllium, lithium, beryllium, carbon atoms everywhere, and nitrogen all through the air, oxygen so you can breathe, and fluorine for your pretty teeth, neon for the pretty signs, and all that time, and sodium for salty times, magnesium. I can do all the rest. I just have to think about it, and of course now thinking about it, I don't remember it. Okay, 3,200. Let's go to 10,000 at 25 seconds and do that, and we'll see what we get. All right. Okay. I'm moving around too, so hopefully I didn't bump into anything. Even though I got the light of the screen, it's actually kind of dark in here. Now, so we're doing the Eagle Nebula again, and I think I see. Oh yeah, you look at that. Can you see that? Wow. Okay, you look right at the center. You can see now that there's a sharper contrast between the darkest lane in the center and the brighter nebula behind it. Isn't that cool? Isn't that cool? Wow, that's so nice. Now, for those of you that saw on my Facebook site, you saw the Juno Jupiter images and how I processed those. Those came from the raw files from the Juno spacecraft. Okay, it wasn't from NASA. It wasn't a process photo I put up from NASA. I processed those from the Juno raw images that are available that you can get. So when I look at something like this, okay, this reminds me of the Great Red Spot photo. They kind of look whitish and hazy. But then you saw the process section I did of it, and what did it look like? It looked gorgeous. You saw all the detail in there. Well, I can take this and do the same darn thing. Let me just check my settings. It's 25 seconds at 10,000. Yeah, we're going to stick with that. So I'm going to do another one of those. Now, you'll notice there's a cluster in the middle of this too. That cluster of stars is, of course, a cluster of stars that formed in the nebula. And they are also responsible for lighting up the nebula. Now, before a star, and we call it winks on, like winking, before a star winks on, which means that temperatures reach several million degrees, enough of millions of degrees so that fusion could take place, until a star actually winks on like that, one more. Until a star winks on like that, the nebula is going to be dark. Before the first star winks on, the nebula is just going to be a dark gas cloud in space. But then as soon as it winks on, we see something like we see here. We see something like we see in the Lagoon Nebula. We see something like we see in the Trifid Nebula. Okay, at least the emission part of it. So that is how these nebula light up. Okay, and otherwise we don't know if there's any nebula out there other than to take a spectrum of the area of space, and see what we can see, if there's anything to see. Yeah, see that right there in the center. There it is again. It's nice and nice delineation there. So I'm going to take several photos of this, and then I'm going to process them in the same way that I processed the Juno Jupiter images, and we'll see if we can actually get a better view of the Eagle. And of course, I'll make this available to you along with these photos I'm taking here. You'll get the raw photos, and you will also get the processed photos after. You can email me, just so you know. You can find me a variety of ways. If you go to my website, okay. Now that's the other thing. We have several websites now. The actual website for my company is FX, as in Frank X-ray, FXModels, MODELS.com, FXModels.com. Right in the center is the email address, and it's info@fxmodels.com. You're all free to write me. You're all free to email me and ask questions, and I'll be happy to get back to you. The other thing is, if you go to the one-stop shop site for all of our streaming, that's called the astroimaginglive.com. That site just came up yesterday, and we've been working on it fast and furious, trying to get it up and running, and it's running beautifully now. And there's just a few little tweaks left to do, and then that is going to be something where we actually can show you right there on the screen in front of you all three of our streams. You're going to see Paul and Keith at P&K Space Imaging on the left. You're going to see SkyTour LiveStream in the middle, and on the right you see Bill New York Skywatcher. Now, you can watch all of them if you want to torture yourself with all the sound and music and talking that may be going on across all three, or you can click on each one and then click the maximize little square down at the lower right of each of those panes where they're shown, and bring up the main view on YouTube, because that's where these YouTube channels are located. If you're done with it and you want to get out of it, all you have to do on YouTube is hit escape on the PC, and I'm not sure what you do on the Mac. You just hit escape on the PC, or you re-click that maximize square on the lower right, and it will bring you right back to our website. And then from there, there's a main chat for all three sites right there below all of them. And then we will have there's a gallery up there that you can find when you go up to the top menu under the name astroimaginglive.com. There is there's a menu, and under that menu you're going to see home, about, services, contact. We didn't put anything in the contact yet because we haven't figured out who wants to be the point of contact. I'm okay with it. I'd like to be, but we just haven't talked about it. And this is a democratic site. You know, we're trying to make sure that everybody gets a say, because it's going to go beyond Paul and Keith, me, and Bill. It's going to eventually get to another guy that is in the southern hemisphere, who's going to be looking at southern hemispherical stuff. Now, he may be able to see the Lagoon Nebula straight up over his head. So the imagery you're going to get is spectacular. It will be spectacular. Again, he has to have a similar camera to mine. He has to have a similar setup. If he doesn't, then we'll just get what we get. But we're actually, we kind of went through, we talked to the guy. We actually are going to set up a conference call with him and set him up, because we want to have an astronomical system set up so that we have full sky coverage, so that even at noontime here, my time, we should be able to get to some dark sky somewhere. Now, what I'm using as a model for all that is something called SLOOH, S-L-O-O-H. SLOOH is a consortium of telescopes on Mount Teide in the Canary Islands and in Chile, and I was a member of this for many years. But then they started raising the prices. So what it is you buy time on a telescope, and then you can go take pictures of anything you want. Sounds great, except they only had 5 and 10-minute exposure times. They didn't allow you to customize the views. They didn't allow us to do what you see me doing here. Change the exposure a little, tune it for the best thing. And many times you would just get a generic kind of, I call it a sloppy view of an object, and you miss a lot of detail. Some of it's overexposed, some of it's underexposed. Sometimes you don't even get the right thing, and that kind of thing is something that I just didn't like and I couldn't tolerate. So over time I said, all right, you know what, I love SLOOH. I've been in it since the very beginning almost, but I'm gonna move on. And it turns out there's another telescope system, a set of systems that you can get involved with. It's called Las Cumbres Observatories, and Los Cumbres is not just one observatory, it's a consortium of like 15 observatories all over the world. Look, my battery was exhausted. I guess it's tired of me talking. I'm going to change the battery. And the Los Cumbres observatories actually have a variety of instruments, a variety of ways to get your data, and you can actually you put in what's called a proposal. And when you give them a proposal, you can then get pictures taken the way you want them, exactly the way you want them, no more and no less. And I think that's kind of cool. And as we move forward, I'm probably going to start working with Los Cumbres a little more. I don't even know if I know people there. I may, because there's like 14 or 15 observatories around the world. I certainly know some people somewhere. So it'll be kind of cool to get photos from these different observatories. And we're talking about telescopes that have diameters minimally a meter in diameter. Okay, so we're talking big observatory instruments. So it's pretty cool. Now, I'm just going to check the... Okay, good. We are doing okay, dew-wise. We're not getting too much dew left, or coming up. And I know I'm stuck on the Eagle. I'm gonna move off the Eagle here in just a couple minutes. I figured while I have you, I'm gonna kind of show you what it is that we do. You know, what it is we get when we do this kind of thing. Now, the other thing I'm gonna do is I'm gonna actually show you something else. I did this the other night, all right, and we're gonna go there now. So I'm moving, and we're kind of near the area that I want to look at. So we're gonna look at this, do a recording, get up into the higher realm. Oh yeah. Now look at that. See, this is something that was by request one night, but I'm doing it again here because it's actually just fabulous. This is actually something called M22. All right, and M22 is actually a globular cluster, and we don't need to be. I'm going to go down to 1250 ISO for this, and we're going to do this one in 13 seconds at 1250 ISO. Alright, just to see what we get. I want to see little tiny pinpoint stars. I don't want to see bloated star images. So sometimes you tune the exposure. So what I'm saying is sort of a rough idea. Clearly this wasn't enough, but when we zoom in, we can see if our focus is good or if we need to critically focus again. Yeah, it looks pretty good right now. So what I'm going to do is we're going to go a little bit longer. We're going to go to 20 seconds, and we'll change the ISO to 2000. Okay, so here we go. Okay, so this is 20 seconds at 2000 ISO on a globular cluster in Sagittarius called M22. It's a beautiful cluster. I know that looked kind of faded what we just saw, but check this one out. Watch this. You ready? Here it comes. Oh, it's coming up. I haven't seen it yet. I'm just kidding. That's pretty nice. Okay, so let's take a look at that. So there you go. It's a fairly big cluster. All right, and M22 actually, just to give you some basic information about it, M22 is 10,000 light years away. That's 10,000 light years. Okay, and again, if anyone's interested, at 10,000 light years away, it's also 32 arc minutes across. Okay, so multiply that by 60 to get the number of arc seconds. Okay, and you're going to be able to then figure out how big it is in light years. All right, so M22 is really, it's considered one of the finest globulars in the sky. We're going to take a couple higher ISO rather pictures. We'll do ISO 3200 at 20 seconds once again. It's really considered to be one of the best ones in the sky, and it actually is. It's distinctly elliptical in shape. It's not quite spherical, and that's what's interesting too about it. And it's actually, if you think about it, when I told you how big it was, at diameter it was at 32 arc minutes. That's kind of cool, isn't it? Because the moon is what, half a degree, right? Well, what's 30 arc minutes? Half a degree. Okay, because 60 arc minutes is a degree. So when we look at this, we're seeing something that there is actually slightly larger than the full moon. And I think that's a really cool thing. Now, what's also interesting is those stars you see in the center, those stars that are all around this, you'll see there's a healthy selection of some orange ones or some bluish ones. This is really one heck of a swarm of stars. And these globular clusters, all those stars you're seeing, have been there for many billions of years longer than a lot of the other stars in our entire galaxy. And that's for many globular clusters. Globulars are kind of ancient. They're filled with what are called population 2 stars, which are what are called metal poor. The universe didn't have a whole lot of metals in the interstellar medium. Metals are anything other, in astronomy terms, are anything other than hydrogen and helium. So when we look at stars like this, we're saying, wow, these stars have been here, have been here for so long that we can tell that because they haven't had any, there's no metals in them, no other materials other than hydrogen and helium and a little beryllium. So when we look at these stars and see that these things are so ancient, what it means to us is that they formed at a time when really all there really was hydrogen, helium, and a little beryllium in the universe. And so doing so left them as barren of these other elements. So they may be massive, and they may be they may be a massive cluster, but the cluster is not very well populated by any metallic stars. So there's a dearth of that there. So what does that tell you about planetary formation inside of a globular cluster? I think you're seeing now. We don't expect to see many planets in formation within stars of globular clusters, because as big as they are, hundreds of thousands of stars, as many as there are in a globular cluster, there isn't enough materials of other types to make planets. We're not going to find silicon and iron and so forth. Now, when these stars die, there's certainly going to be plenty of planetary nebulae, but what are they going to have in them? These planetary nebulae are going to have mostly hydrogen and helium. The remnants of this gas, whatever's left over from the ending of the nuclear fires. So we're not going to see a whole lot in these types of clusters, okay, for planets, and that's kind of a sad thing. Now, if we I'll leave it on so we can check it out. Okay, there it is, the full size. So when we look at that, okay, we see that we're talking about M22, again, being one of the most fabulous clusters in the sky. M22 is probably also not going to have very many planets, and that's kind of cool. It's really cool to understand and to see it. Now we're going to go back to something we saw earlier tonight, just to quickly get a photo of it, because it's in a good spot, and we hardly have to move the dome at all, okay? And that, of course, is this guy. Do you know by now what this is? It kind of looks like the same region as the Eagle, but we're actually at the lagoon. I just want to take a picture of the lagoon here. 20 seconds at ISO 5000. Here we go. I warn you, if it comes out really good, I'm not gonna be in control of my emotional state. I might really just go crazy, because the sky is fairly clear over there right now. Let's see what we get. Oh, I'm nervous. I hope this comes out good. Ooh, come on, baby. Show me what you got. Boom, let's go. Oh, talk about a winner of a picture. Look at that. We got a faint satellite heading over the top of the Lagoon Nebula. Is that not the coolest thing? That is so cool. And that was 20 seconds worth. Now, I'm going to move us over just a little more. Other way. And move us down a little bit. There we go. Let's do it again. That was so cool. That picture will be available, don't worry. Is that not cool? That is just so cool. I thought that was neat. So we got a satellite. So even now, where you don't expect that we should see satellites, or have the ability to see satellites at 12:30 at night, where basically the sun is exactly on the opposite side, you'll see that there's actually enough light that we can still see them, huh? There's enough penetrating light, and it's not reflected light off the ground or anything like that. We actually see these satellites from you know, because there's enough light up there that's moving across the Earth's terminator from the perspective of the satellite, that we would see them. Look at that. That's incredible. So as I told you before, right there in the center, okay, we need to maybe do a little critical focus there. That's actually an O star that's powering this. And let me get us into the center now. And move us down a little bit. I'm going to focus right now. So, time to critically focus. Here we go. Yucky. Looks a little better. I know it doesn't look all that different to you. But trust me, I'm an astronomer. I know what's going on. Not really. I'm trying to do my best. I can be just as bad with it as anyone else. Alright, let's do a 25-second photo at ASA 5000 here. Okay. Now we'll see a little bit more detail, and I'm hoping that the detail we can see will not include dew. Let's take a look. Okay, it looks like the corrector plate, the glass is still clean of dew. That's good. Wow. And this is at 5000 ASA. I mean, I could increase this a little bit. Whoops. Oh yeah, look at that. In the center of that pinkish area, that is a O star, Herschel 36, that's actually illuminating that nebula. And you can see it kind of illuminates it spherically. The dark areas, those dark lanes that you see, those dark lanes that, you know, we actually see one. Here, moving across the image from up here down to here. So from upper left to lower right. That dark lane is actually a molecular cloud that's actually between us and the rest of the nebula. So that's what makes it look like it does. That's what makes it look like it has this lane running through it. But that could actually be, just be something that's along our line of sight. Okay. So I think that's pretty cool. Let's see now. I know that there's several other things out here that are kind of cool. And I think I want to actually try and see if we can. Okay, now it's because it's right at the zenith and it wasn't before, and it was in some clouds. I just want to try and take a photo of the Ring Nebula again, guys. I mean, this is just beautiful. So let's go to the Ring Nebula real quick and try to take a picture of it. Okay, there it is in 4K video coming in. Nice. Good, the telescope's aligned in that beautifully. Alright, and now I'm just going to go, I don't need that image. Oh, let's do this. Let's delete that. And now let's come back and do a 25 seconds at 2000 ASA. I want to see what we get. I'm trying to discern some of the fainter details on the outside of this nebula, outside edges of the nebula. Now it's as close to the zenith as it's going to get, and we're looking through the least amount of air right now. That's called air mass. We have a very low air mass above us right now, meaning that there's not a whole lot of thickness of atmosphere between us and our target. So it will be seen as best as it can be once we get the right exposure settings. So let's zoom in and see what we got. Yeah, I moved a little bit. You can see it, I did. Yeah, that was a geostationary satellite that we were picking up there. They tend to move a little. Let me go back and I'm going to go up a little on the ISO sensitivity. I'm going to go to 3200 and stay at 25 seconds. Let's go there. There we go. Now, we talked about the ring before, but I want to just reiterate, the shape of the ring is due to the fact that it's like if you were taking your hand and make like a cup, and make a cup shape with your hand, like you cup water. If you put that, if you face it toward you so that you're looking through your fingers at, you know, the wall beyond or whatever, you can see through your fingers, all right? And if you move it to the side, as you're about to go around toward the back side of something, as if you're circling around a spherical object in front of you that's levitating in space, as you move your hand around to the side, you can't see through your fingers anymore. You're seeing through thickness. You're seeing through an edge, so to speak. And that's what that's like this here. When we see the Ring Nebula here, we're actually looking through some thickness like that. And that thickness that we see causes the Ring Nebula to look a little bit thicker and denser. Okay, but there's still stuff between us and the central star in that hole. Okay, there's still stuff they're still in the hole, but we're actually looking at we're actually seeing the perspective of looking through more stuff on the edges. So like when you're turning your hands around, when you go to the back, you see through your fingers again. When you come to the front, you see through your fingers. When you go to the side, you don't see through your fingers. When you make that cupping motion, like the shape of a circle like that. So that's kind of how this came to be. I'm going to 5,025 seconds. Again, I'm trying to get the outer fringes of the nebula. So 5,000 ISO sensitivity and 25 seconds. Let's see what we get. Meanwhile, I'm going to be looking for other things to go look for. You know, hey, you know, I'm not going to take advantage of it while I'm here, right? And Keith from P&K Space Imaging just sent me a message, and he's probably going to ask if I want to come in on the stream, and I don't think I do. I'm having too much fun. Okay, let's go. Okay, there we go. That's our... Alright, that's interesting. So, there's two things you think about when you're trying to observe for a night. You have something called transparency and you have something called seeing. Transparency is the steadiness of the night and how transparent basically the sky appears. Then we have the seeing, S-E-E-I-N-G, the seeing. The seeing basically depends on what aerosols and other things are in the air. And transparency and seeing are kind of, sometimes people use them interchangeably, and they're not. They're actually separate things. But I always had to, when I did my studies in the observatories, I actually had to always make note of the transparency and always make note of the seeing. And I always had such trouble trying to figure out, well, is tonight good seeing or not good seeing? I don't know. Kind of hard to know. But on a night like tonight, I would say that the seeing is average and the transparency is also average. Snapple iced tea again, sorry. Now, what that means to me is that when we actually have I know you heard that. Let me just go check. I'm sorry. What's Keith asking me about? Let's find out. Oh, okay. They're going to go live around 1 a.m. And he's real excited because we actually are going to have 2 streams live on astroimaginglive.com, and that's pretty cool. Thanks, Keith, for letting me know. I'm sure he's listening in. And because he heard me say that, I thought maybe he wanted me to come on, and he said, "Oh, by all means, continue your stream. We'll have 2 streams going live on the site, so it'd be pretty cool." So let's take a look now at the outside. Let me look at the cloud situation. Oh man, it's so pretty out here. It really is beautiful. I see lots of Milky Way. I see. Oh, it's just beautiful. But the seeing and the transparency stink. We don't have anything like we had that one night where we were together for a little while. It is humid, and humidity will affect how things look. No doubt about it. Now let's see. I don't want to go back to Cassiopeia because that's where I got due on the telescope. All right, let's try. Will I be able to see that? Let me center this. I'm looking at another planetary nebula, trying to see if it's something that we'll be able to actually see. Oh, maybe so. Yeah, let's go there. All right, we're going to go look at another planetary nebula. Yeah, we're not in clouds right now. It's looking pretty good. Okay, so let's check this out. Okay, you're gonna, if we can capture this properly, you're gonna see something very much the same as the other blue object we saw, I believe. And I'm gonna just do a quick acquisition image, 5 seconds at 5,000. I didn't see it. Did you see it? I'm looking. Oh yeah, there it is. It's at the bottom. So, oops, sorry. So now what I have to do is just bring it up. This is called the blue snowball. Go figure. Okay. Now, I know it looks kind of mundane, right? I don't see much there. And if we do a... okay. I'm actually filling up the memory card. I can't believe it. That's crazy. Okay, little housekeeping. Sorry. Little housekeeping here. I'm not going to delete any of the. Imagery that we've taken, but I am deleting some of these early images. These are actually way back from the very beginning. I should have deleted them, because they're eating up many gig on the card. Again, 4K is basically more than twice, sometimes up to 4 times the actual usage on the card. Okay, so that should be good enough. Now let's just do another, 5 seconds, 6 seconds at 5,000 on the blue snowball. Okay, and it's right there in the middle. Let's take a look at what we got. Come on, hey. There we go. Now, again, I'm trying to get it, set the optimum exposure for you right away. This is kind of cool. Now, we need to mess with this just a little bit. The blue snowball nebula does look similar. Now, you're seeing a trend, aren't you? Planetary nebulae many times look bluish, don't they? Well, if you're interested, you want to do some homework, go look up why planetary nebulae look blue. The Dumbbell Nebula M57 has some bluish green. What causes that? Why is there blue in these nebula? Right? And the answer will be very interesting. And we'll get to it if you once you actually make an effort to check it out. I think it'll be pretty cool to see. Now, we don't know too accurately how far away this is. It's 3,600 light years, roughly. But there's some huge disparity in some of the estimates. So, you know, sometimes some say it's 1,800 light years even. But, you know, that would make its diameter like 20,000 astronomical units in diameter. But another survey says it was 5,600 light years away, and that would certainly make it about 50,000 astronomical units, or actually 0.8 light years, almost you know, just over 3/4 of a light year away. Remember that magic number we used when we converted to AUs? The AUs per light year, 63,200 and change. Okay, 200 and something 0.1, if I remember what it was. And well, that number of astronomical units is pretty interesting. Now, in this little pretty nebula, you can actually see that there's a little interesting brightening going on in it, and there's a little dark area. That's actually systemic. That is something that belongs there. It's something that was really kind of cool. And I'm going to go down to 2500 ASA and just go up to 8 seconds. So go down several stops and come up only one. So we're going to get a little dimmer image, and let's see at 8 seconds at a lower ISO rather, if we can actually see some more detail in there. The key is the lower ISO. Lower sensitivity means that you have a better view. Yeah, it's still pretty faint. Still pretty faint. I can monkey with this over time and get something, but you know, in the interest of keeping on and keeping on, let's just keep going and see what we get. Now, there's another object that's coming up that is something that I know everybody really likes, and it's actually pretty good. And it's right near us right now where we are. And that is the Andromeda Galaxy. Yes, the Andromeda Galaxy. We're going to go there. Because why not? We're already nearly there. So we're going to go look at the Andromeda Galaxy, so we can see stars that are already at the height of their formative years and are actually you know, just going around a galaxy that's several million light years away, 2 million in fact, and that's incredible. And incidentally, if you didn't know this, maybe you do, the Andromeda Galaxy and the Milky Way are heading for a collision course sometime in the future. Okay, 13 seconds at 10,000 ISO sensitivity. Let's see what we got. I couldn't see it in the view, so I have to take an acquisition photo to catch it, and then we can work around it. Should be on the bottom. Yeah, it's down the bottom. Okay. So now that we see it's there, I'm going to bring it up. And if I do a 4K quick video of this thing, there we see it now. And we can bring it up. See, this is why the 4K video is really helpful here. We can actually use it to set the object in place. Okay, that said, I'm now going to go view the video I just took and delete it, because it's just an acquisition video on 4K conditions. And now let's do a nice little photo of the Andromeda Galaxy. This is a galaxy that's, like I said, 2 million light years away, and we actually can see a tremendous number of detailed objects within the galaxy, that is, other star forming regions. Whether we'll see them with this telescope is questionable, because it's not high in the sky yet, it's still low in the murk. I don't have any doubt that we could. So here's 15 seconds at 40,000 ISO sensitivity. Alright, and we're going to check out what we can see. Now again, this is the angle at which I have wind coming through the shutter opening, and that wind is laden with moisture, so it is going to deposit dew on the telescope, and apparently more than I thought, as you just saw. Let me just look at it. Oh yeah, it didn't take long. So once again, because I never say die and I never say quit, I'm gonna plug in my handy dandy trusty little hair dryer that sometimes doesn't work, and let's see if we actually get it to work this time. Yeah, it's starting to work. And by the way, just so you know, the moon has just risen. So the moon is in what's called last quarter, and I'll show you the moon. It really is pretty. I mean, what night's complete without looking at the moon, at least for a couple minutes, right? Yeah. So, hopefully you'll share this stream. If I can get a good shot of the Andromeda Galaxy, it'll be a miracle now, because we do have the moon out, and the moon is already brightening the sky. I wondered what was happening, and I just realized now, well, it's the moon, dummy. Okay, sorry, I didn't know. I lost track of when the moon was actually going to rise, so I apologize for that. But let's just try one more time to get a good photo. Now, if we look at this, you see it's really just too bright. So we're going to delete that. And it's that bright because, of course, I didn't realize that we had to worry about the moon yet, and we do. So I'll just do 5 seconds at 40,000. Let's see what we get. We probably are going to get a fairly bright looking object. So yeah, that's not bad. Okay, so you can see that you can start to actually see some dark lanes within the Andromeda Galaxy. That's really cool, and the galaxy is so big, it literally it moves. It's almost 5 degrees in the sky or so. So yeah, with total all-encompassment that's out there, it's just incredible. So I'm going to go drop the ASA down to 16,000, but bring up the exposure, which will be 13 seconds at 16,000. And then basically the exposure is not going to look very much different from what we just saw. It's because it's a one-to-one relationship. You go down 2, you go up 2. You go down 2 stops, you go up 2 exposure settings. And see, we get a finer resolution because we don't have as much noise. So let's take a look at that again. This is what we have right now. Okay, and you can still see some noise in that image. It's that kind of, it's that modeling that you see throughout. But now let's go back and let's go down to 1, 2, 3, 4 more stops to 6,400. And then we're going to raise it by 1, 2, 3, 4 stops to 30 seconds. So this is about the max I probably want to do with the Andromeda Galaxy, especially with the moon having risen. And the moon just is clearing the trees now. So by the time we finish this exposure, we'll be able to check out the moon as an object for tonight. So again, let me know if you guys are having a good time. I'm going to actually read through the chat, moving forward here a little bit. And if you guys have any last questions or whatever, then I'll be happy to answer them. I do have the chat kind of stuffed on the bottom of the screen, so I don't see it all yet. Oh yeah, this looks pretty nice. Check this out. So at 6,400, this is what we got. Now you can actually see a dark lane there in the Andromeda Galaxy. And if you look at where that actually is in the nebula, in the galaxy rather, you see that it's actually a lane that is kind of close to the center of the nebula. And I call it a nebula, but galaxies are actually called nebula, but it's kind of weird. It's kind of close to the center of the galaxy in the photos, so there's a lot more galaxy out there to see, pretty much so. And so it's really cool. We will view this again. I do want to try and see if we can see one more object. I'm going to go to it now. I'm moving. It might be... Oh, it's visible, but I don't know if we're going to actually see it. Let's find out. It's another galaxy, but it's fainter than this one by far. Okay, this one's called the Pinwheel Galaxy in the constellation of Triangulum. Um, and this galaxy is notoriously low surface brightness, it's called. But we'll try it. Let's do 30 seconds at 6400 again. It's going to be down near the bottom. We'll probably have to move it up, but I got to try it. And this galaxy here is the famous pinwheel galaxy in triangulum that everybody knows about. And this one is, well, this one's 2,800,000 light years away. So it's a little farther than the Andromeda galaxy, and so it's quite a distance. But there's some really blatant star-forming regions known as the H2 regions I told you about in this galaxy. And again, the galaxy is down near the bottom. I gotta bring it up. So I'm gonna do that. Just one last try here. Just 1 second here. Let me do this. Alright, and now instead of 30 seconds, we're going to come back off of that to 15, and I'm going to go up to 12,800 ISO sensitivity for 15 seconds. And let's see what we got. I just don't want to, you know, keep you hanging much longer and have you. I want to show you the moon. It's going to be beautiful. The moon is going to look nice tonight. Yeah, see, the moon is causing this bright imagery. Sadly. I mean, you can see the galaxy, it's there, but it's really, really blotted out by the bright moon. So, with that said, why don't we just go take a look at the bright, bright moon. And I'm going to set this up ahead of time. Let me go set up my, my camera here to basically do a we'll start with a 50th of a second at 100th, and that is a 100 ISO. So in other words, a setting you can't use for anything but the moon. Here we go. I don't know if this is gonna work. Wow. Oh, hey, are we good or are we good? Look at that. That is just so beautiful. Interesting. Very, very, very interesting. And in the last quarter of the moon like this, it actually is really pretty. You can see some really neat, you can really see some really neat features. I'm gonna do critical focus again, by the way, just shortly. Let's go over here. It's so close to the horizon, you can actually see, you know, this undulating going on, and that always looks worse. Let's focus this. So out of focus, in focus. Okay, now as a matter of scale, that crater right there that you see, that's called Plato. Plato is a flat bottom crater because it was filled with lava after impact. And it's 60 miles across, that little crater right there. Okay, and Plato is a sort of a crater that people learn first. You know, it's one of those ones that people learn first. You also noticed, and you probably are asking in the chat, you see that bright area over to the left. So let's go over there and zoom in on that. Okay, hold on. Okay, let's do this now. Let's zoom in. Okay. Okay, so this object here, this crater, that high-pitched whine you're hearing is the hand controller, which is giving us some issues with the wireless mic. There we go. Okay, now you see all that undulating going on. I'm not actually sure what this crater is, But, you know, we can actually figure it out. I think... Okay, what just happened? Okay, I'm not sure what just happened. Are you still with us? Let's see what happened here. Yeah, you're all still here, correct? I don't know what happened, where that went. I think maybe that was some kind of... I had a glitch come up on the screen, so that's why I'm looking here. But it appears that the glitch was only for me in the observatory. I don't think it came from you. Yeah. Is that Aristarchus? Is that what you're saying? I'm looking at the quote now, finally. I'm reading your comments, by the way. Yeah, F-47. I know it's not a nebula. Okay. And it's not because I'm old, and that's why I'm saying it, because I'm old. That's not why. I was actually just saying it because that's actually historically what they were called. And yes, it's so 20s. I get it. Okay. But, you know, it is what it is. In my astronomy career, we've actually... we called things nebula that people would shake their heads at and say, what? And it has nothing to do with age. It has to do with, you know, current understanding. Yes, I know that galaxies were called nebulae. In fact, I have a I have a book from the 1800s that I wanted to actually read some passages to you guys about, which I can't find it. It's actually called The Architecture of the Heavens and a Series of Letters to a Lady. And it's the coolest thing because back then, astronomy was sort of frowned upon. It wasn't actually a science that was taken seriously. So the only way they could actually get their points across was to do it with some poetic prose and you know, make it as if you're showing the wonders of the universe to a lady. I know that sounds so crazy, but that's what they did, and so that's what the book was about. This is before they even knew that galaxies were separate, spinning island universes of stars all their own, you know, kind of a thing. Island universes is my phrase to describe basically galaxies for people who you know, see them for the first time. Wow, this is just a beautiful view. It looks like it froze just now. Oh no, it didn't. Okay, maybe I was freezing. Okay, neato. This is good. Okay, so. Oh, I see Keith was visiting. That's cool. Hey Keith, how you doing, man? Let's see now in the chat. Okay, I guess obesity is the question of the day. Yeah. Well, anyway, I think that, you know, I think that we're doing just fine. Now I'm going to go over to the Terminator because I'm going to try and locate as we go toward the Terminator. You can see sometimes you see some craters that are actually just barely being illuminated. And because it's near the horizon, okay, you notice that because it's right near the horizon, sometimes you actually see, that is its horizon. I'm sorry, the Earth's horizon. Because the moon is near the horizon, you actually see some interesting artifacts and some strange goings on the moon. But I get UFO cases where people send me imagery and say, look, this isn't supposed to be there. Yeah, well, no, of course it's not supposed to be there. But I believe it's what you're seeing is actually something that was illuminated by the sun, and then because it was low to the horizon, you actually saw some artifacts caused by the turbulent air mass in our atmosphere. And who knows what that turbulence is called? And Daryl, I think you're right, by the way. I think that it was Grimaldi that they were talking about. So when we see this turbulence like this, all right, and you see something right now, like you see if we look at the crater that's almost centered, you see there's like a little strange light in it. Okay, that is something that could easily be mistaken for some type of sentient life form on the moon. But in fact, that's just an area of a raised area on the moon that's catching light in a particular way, and because it's almost a very tiny peak, it ends up looking like a thing glowing all its own, but it's really just a high peak, and the light plays off of small things in stranger ways than large flat planar things. Like you don't see any of that. You see shimmering going on over the Maria to the left of that object, but you do not see, right? You do not see any. You don't see any of the attendant visual artifacts. I'm seeing visual artifacts now. When I look at that object on the screen at the center of the crater, on one hand it looks like it could be an uplifted area on the moon. On another, it looks like it could be a geostationary satellite seen against the moon. And the satellite's 22,000 miles out, say. And the only way to know is to actually find this on other imagery and see that it's there at this time of the lunar cycle. Or, the other way to do it is to actually take some photos. And I'm going to just take a couple of photos of it. And this will be at 50th of a second, and it goes out to the full-size moon. And then we have to zoom in again to look for them. And I forget where this was. Sorry, I actually, I didn't see exactly where I was. I can zoom in again. Oh, there it is, I see it. Okay. Alright. Now again, I'm pretty sure that's actually on the moon, just so you know, but what I'm trying to do is establish, let's see, go up here and go up there. Okay, that's that one, right? Okay, now, okay, now when we look at this, you can see that that object now appears to be another crater that we missed seeing before because of the issues with the live view of the moon and with the atmospheric scintillation. So that bright spot, okay, is actually another crater within that other crater. So it just took a sharp photo to show, because the photo captures it in a moment in time, which I think is pretty cool. So that just illustrates, for instance, how we take imagery and use it to our advantage a lot of times, and that's just what we're doing here, trying to make sure that we understand exactly what an image is telling us. Okay, let's see here. I'm going to get to this. Yeah. Oh, I didn't see the whole thing, Daryl, that happened between you and that other guy, but thanks for taking care of that, by the way. Yeah, there's always a few. There's always a few. Yeah, this is just something else, man. I'll tell you. I love it. I love it very much. And I tell you this, there's nothing like it. Nothing like real, true astronomy. Nothing like it. So I hope that you guys enjoyed this for what it was. I know that it's we're actually kind of coming to the end of tonight, and I hope that you actually enjoy the views now. And now P&K is going to be starting up looking at the moon. So I encourage you to go over there. You can go to astroimaginglive.com. That's astroimaginglive.com, and pick the P&K space imaging site. Or you can go to the P&K Space Watch, sorry, P&K Space Imaging. I know I call it Space Watch, it's not. P&K Space Imaging YouTube channel, which you can get to from mine because I have it cross-linked, and you'll be able to take over and watch the moon for the rest of the night. So it'll be pretty cool. Now, hopefully, you will be very hopefully you'll be very pleased with what you see over there. And I think that maybe over here we're actually kind of done for the night. So I just want to say thank you so much for joining me here on the SkyTour live stream for this night, July 16th. It's actually July 17th now. No, it is the 16th. Sorry, it was the 15th before. Wow. Hey, what can I tell you? I'm screwed up. But hey, tell all your friends. If you have questions, leave them for me in the comments under the stream. I'll be happy to answer them for you. Also, you can go to my website, fxmodels.com, and see my email there. Write me any questions you have. And you can also go to our astroimaginglive.com and our individual stream sites if you like, and leave comments on those videos as well. Hope you had a good time tonight. We investigated stellar nurseries, planetary nebulae. We even saw a little bit of a supernova remnant. We've got a ways to go before we can really see that. But thank you for joining me, guys, and I'll see you next time.